Hello, and welcome to the Snoozy Scientist, where we explore the biggest questions in the universe, one sleepy yawn at a time. Wherever you are in the world, whether in a quiet bedroom, under a blanket of stars, or tucked away on a rainy night, this little corner of calm was made just for you. A peaceful place where science, stillness, and wonder sit side by side to put you to sleep. Tonight, we're setting out on a journey, not just across the cosmos, but backward, to the very beginning, or rather, what we thought was the beginning. For over a century, the Big Bang has been the story we've told. A single moment where time, space, and energy exploded into existence. A blinding burst that became stars, galaxies, life, everything. But recently, some scientists have begun to question this narrative. What if the Big Bang wasn't the beginning at all? What if it was just a turning point, a middle chapter in a much older story? Could the universe be older than we can measure, maybe older than time itself? Could it have emerged from the collapse of a previous universe, or has it always existed? Infinite, eternal, without start or end. As strange as it sounds, there are clues, because while the Big Bang explains a lot, it doesn't explain everything. Not the uniformity of the cosmos, not the silence before the signal, not the patterns that hint at something deeper. Tonight, we'll press gently against the edge of what we know, exploring theories that stretch the imagination and maybe even reality itself. Ideas that ask us to reconsider the very fabric of existence. But before we begin, if you enjoy calm, thoughtful science that helps you fall asleep a little smarter than you were before, it would mean so much if you gave this video a gentle like and tap subscribe. It helps others find this quiet little corner too. And if you're listening from somewhere special, let me know in the comments. Where are you? And what time is it right now? It's always a joy to see how far this snoozy science community reaches. Now take a deep breath, let it go, and let's begin. When people hear Big Bang, they often imagine something loud and violent, an explosion that shattered the silence of nothingness and threw stars into every corner of space. But in reality, the Big Bang was not an explosion in space. It was the expansion of space itself. And it didn't happen at one point in the universe. It happened everywhere, all at once. To understand what the Big Bang Theory actually says, we have to start not at the beginning, but with what we see now. Look up at the night sky, and every star you see belongs to our galaxy, the Milky Way. But beyond that, through telescopes, astronomers have found that all distant galaxies appear to be moving away from us. And not only that, the farther away they are, the faster they're receding. This discovery came from a man named Edwin Hubble, who in the 1920s measured the light from distant galaxies and noticed something strange. Their light was stretched, shifted toward the red end of the spectrum. This phenomenon, known as redshift, is similar to the way a siren drops in pitch as it moves away from you, except instead of sound waves, it's light waves being stretched by distance. Hubble's measurements led to a remarkable conclusion. The universe is not static, it's expanding. Space itself is growing, like a balloon being slowly inflated. And if space is stretching now, that means it must have been smaller in the past. Rewind the clock, and you arrive at a time when everything, every atom, every particle, every speck of matter and energy was packed together in a state of almost unimaginable density. This is where the idea of the Big Bang comes from. It wasn't a bang in the way fireworks burst across the sky, but rather the moment when space began to expand from a much hotter, denser state. Not a violent eruption, but a smooth and rapid stretching, a swelling of the fabric of reality itself. The theory gained more ground in the 1960s when two scientists, Arno Penzias and Robert Wilson, accidentally stumbled upon a faint, persistent hiss while working with a radio antenna in New Jersey. No matter where they pointed their equipment, the signal was always there, quiet, uniform, and coming from every direction in the sky. At first, they thought it might be bird droppings on the antenna, but it wasn't interference. What they had found, without knowing it, was the afterglow of the early universe. This mysterious signal is known as the cosmic microwave background radiation, or CMB for short. It's a soft, invisible echo from the early universe, light that was released when the cosmos was still young, about 380,000 years old. Before that moment, the universe was too hot and dense for light to travel freely. It was like a fog of energy and particles constantly colliding, unable to escape. But as the universe expanded, it cooled, and eventually it became transparent, allowing light to move freely for the first time. That light has been traveling ever since, stretched over billions of years by the expanding space around it, slowly shifting into the microwave range, invisible to our eyes but still detectable with the right instruments. What's astonishing is how perfectly the Big Bang Theory predicted this. The existence of the CMB, its temperature, and its near uniformity across the sky. All of it matches what the model says should happen in a universe that began in a hot, dense state and has been expanding ever since. And it's not just the CMB. The Big Bang model also explains the abundance of light elements like hydrogen, helium, and lithium, which were forged in the first few minutes after the expansion began, when temperatures were still high enough for nuclear reactions to occur. This early burst of element formation is known as primordial nucleosynthesis, and the amounts we observe today closely match the predictions made by Big Bang calculations. What's important to remember, though, is that the Big Bang wasn't an explosion into empty space. There was no outside for it to expand into. Instead, space itself was stretching and still is. Every galaxy isn't flying through a fixed cosmos like shrapnel from a blast. Rather, the distance between galaxies is increasing because the fabric of space between them is expanding. The galaxies are mostly staying in place. It's the space itself that's getting bigger. It's a strange idea, but it's one that matches nearly everything we've observed so far. And yet, even with all this elegance, all this predictive power, there are still pieces missing. Mysteries the Big Bang model can't quite account for. Questions that linger at the very edge of what we know about the shape of the universe, its uniform temperature, and how it all got started in the first place. As we drift forward, those questions will begin to unfold, gently, quietly, inviting us to look beyond the edges of the model, into the parts of the story still waiting to be told. Even with all the observations supporting it, the redshift of distant galaxies, the cosmic microwave background, the calculated spread of light elements, the Big Bang model still leaves us with some lingering puzzles. Quiet ones, the kind that sit at the edge of the universe and whisper that something isn't quite right. These aren't questions about how stars form or why galaxies spin the way they do. These are deeper. They ask not just what happened, but why it happened the way it did. One of the first mysteries is something cosmologists call the horizon problem. To understand it, we need to picture the universe in its earliest moments, when it was still very young, very small, and very hot. According to the Big Bang model, space was expanding rapidly, and during this expansion, distant regions of the universe were moving apart so quickly that light hadn't had time to travel between them. These areas were essentially cut off from each other, like isolated islands with no bridges, no communication. But when we observe the universe today, we see something surprising. The temperature of the cosmic microwave background, that faint glow left over from the early universe, is almost exactly the same in every direction. If you look one way and then the other, you'll find that the temperature difference is less than 1 part in 100,000. It's astonishingly smooth. And that's the puzzle, because in theory, those distant parts of the sky were never in contact with each other. There wasn't enough time for light, or heat, or information of any kind to pass between them. So, how did they end up being the same temperature? It's like finding two rooms on opposite ends of a mansion that have exactly the same warmth, even though no heat ever flowed between them and the heating systems were never synced. The universe, it seems, is more uniform than it should be, and the Big Bang model on its own doesn't explain why. But the temperature problem isn't the only quiet riddle hiding in the background of space. Another is something known as the flatness problem. In physics, flat doesn't just mean two-dimensional like a piece of paper. It refers to the geometry of space itself, whether the universe is curved like a sphere, bent like a saddle, or perfectly balanced like a straight flat line. Our current measurements tell us that the universe is incredibly flat, not almost flat, not just a little curved, but almost exactly flat, with just the tiniest margin of error. And here's where the strangeness begins. If you roll a pencil across a table and it's even slightly tilted, the pencil will drift slowly at first, then faster. The same idea applies to the geometry of the universe. If space started with even a tiny amount of curvature, over time that curvature would grow. The universe would either curl in on itself like a closed loop, or expand outward uncontrollably like a hyperbolic sheet. But it hasn't. It's stayed balanced, almost perfectly flat. And for that to happen, the early universe would have had to begin with an incredibly precise energy density balanced to more than 1 part in 10^6. That's a 1 followed by 60 zeros, a level of fine tuning that's hard to ignore. It raises a quiet, unsettling question. Why was the universe so perfectly balanced in the first place? Why did it begin in a state that just happens to keep it flat for billions of years? This precision doesn't seem random, and yet the Big Bang model doesn't offer a clear reason for it. It simply sets the starting conditions and asks us not to wonder too much about where they came from. And then there's one more puzzle. It's called the monopole problem. To explain it, we need to go back to the early universe again, just fractions of a second after the beginning, when temperatures were unimaginably high, and the fundamental forces of nature were still merging and splitting. During this time, certain theories, especially those called grand unified theories, or GOTs, predict that heavy stable particles should have formed. These particles would carry only one magnetic pole, either north or south, unlike every magnet we know, which always has both. They're called magnetic monopoles, and they're predicted to be plentiful in the early universe. But today, after decades of searching, we haven't found a single one. Not in space, not in cosmic radiation, not in particle detectors, not even a hint. If the early universe really was that hot and dense, these particles should be everywhere. But they're not. They're completely missing. And that's a problem, because it means either those theories are wrong or something happened to prevent the monopoles from forming in the first place, or at least from surviving. These quiet inconsistencies, the smooth temperature of the sky, the razor-flat geometry of space, the absence of expected particles, don't disprove the Big Bang, but they do suggest it might not be the full story, or that something else happened in those earliest fractions of a second, something we're still trying to understand. As we move forward, those possibilities begin to take shape. Possibilities that try to fill in the gaps, that introduce new stages in the early universe, that suggest inflation, bounces, or entirely different ways to think about beginnings. And slowly the story continues to unfold, just as the universe once did, quietly, gently, and full of wonder. If the early universe had so many unexplained quirks, if it was too smooth, too flat, and missing particles it was supposed to contain, then something had to account for that. And in the late 1970s, a young physicist named Alan Guth proposed an idea that would change everything. It was a bold suggestion, and it had a name that sounded gentle, even harmless: cosmic inflation. The idea behind inflation is surprisingly simple, but also surprisingly strange. Guth suggested that in the tiniest sliver of a second after the Big Bang, not seconds, not milliseconds, but within a fraction of a moment, the universe didn't just expand, it exploded outward at a speed far faster than the speed of light, not with matter moving through space, but with space itself expanding violently, rapidly, and unimaginably fast. This period of cosmic inflation would have lasted for only a breath, a flicker of time so short it's hard to picture. But during that flicker, the universe would have ballooned outward by a factor so large it defies comprehension. From smaller than a proton to something the size of a grapefruit, or maybe larger, in far less than a trillionth of a second. And yet, that brief moment changes everything. Because if space expanded that quickly, then regions that were once in contact, regions that shared heat and information, would have been stretched far apart, explaining why they still look so similar today. This helps solve the horizon problem, the question of why the universe appears so evenly heated, even in areas that shouldn't have had time to equalize. Inflation also helps with the flatness problem. As space stretched and smoothed out, it would have flattened any early curvature, like pulling a balloon until its surface looks more and more flat from a small perspective. No matter how the universe was curved before, inflation would have ironed out those wrinkles, leaving behind the geometrically flat cosmos we see today. Even the monopole problem finds a possible answer here. If the early universe created heavy particles like monopoles, inflation would have diluted them, spreading them so thinly across the enormous expanded space that they'd be practically undetectable now. Still out there, perhaps, but far too rare for us to find. In a way, cosmic inflation works like a cosmic eraser, wiping away the awkward irregularities of the early universe and replacing them with something smoother, simpler, and more consistent with what we see today. But while the theory solves several major puzzles, it also raises new ones. For instance, what caused inflation to start, and what made it stop? Physicists propose that a strange kind of energy field, often called the inflaton field, may have driven this expansion. This field would have filled space with a kind of repulsive pressure, stretching the fabric of the universe outward. And then, just as suddenly as it began, this inflation would have ended, releasing energy that heated the universe and set the stage for the standard Big Bang expansion we're familiar with. But this leads to another complication, because if inflation can happen once, why not again? Some models suggest that inflation never truly ends everywhere, that in some places it keeps going, endlessly spawning new universes, like bubbles in a cosmic foam. This idea is called eternal inflation, and it suggests that our universe is just one of many, one tiny bubble in a vast multiverse. It's an intriguing idea, and one that opens even bigger questions about reality, but not everyone is convinced. In recent years, some scientists have started to question whether inflation, as elegant as it may seem, is really a solution or just a convenient patch, a fix that smooths out the math without offering clear, testable predictions. One of the biggest criticisms is that inflation may be unfalsifiable. That means it can't be proven wrong. If a theory can be adjusted to explain any outcome, no matter what the data shows, it loses something important: the ability to be challenged by evidence. And in science, a theory that can't be tested or risk being disproven becomes difficult to trust. Some physicists argue that inflation has become too flexible, that every version of the theory bends and shifts to match new observations, rather than standing firm and risking failure. They point out that many inflation models have already been ruled out by data from missions like the Planck satellite, which map the cosmic microwave background with extraordinary precision. And yet, new versions keep being proposed, always just out of reach of contradiction. Others still support it, pointing out that inflation made predictions about the early universe long before those predictions were confirmed, that it successfully anticipated a certain pattern in the temperature fluctuations of the cosmic background, known as scale invariance, a subtle fingerprint that appears to match what we observe. And so the debate continues. Is inflation a brilliant insight into the universe's first moments? Or is it a placeholder, a bridge from what we know to what we don't? As we continue to explore what may have come before the Big Bang and what deeper truths lie beneath the surface, inflation remains a powerful idea, but one surrounded by questions. Questions that lead us further into speculation, deeper into mystery, and closer to the edges of the known universe. And out beyond those edges, other theories begin to stir, each one trying to rewrite the origin story in its own strange and beautiful way. If the Big Bang wasn't the very beginning, then what came before it? It's a question that sounds simple, natural even, the kind of question a child might ask while staring up at the stars. And yet, hidden in its simplicity is a puzzle that has haunted physicists, philosophers, and cosmologists for over a century. Because to ask what came before the Big Bang, we have to ask whether before even existed. According to the traditional Big Bang model, time itself, not just matter or energy, but time, began at that moment. There was no ticking clock before it, no space to measure, no before or after, just a beginning, a moment where everything started and nothing existed prior. This idea is based on the math of general relativity, which, when pushed back to the earliest stages of the universe, breaks down into what's called a singularity, a point of infinite density and zero volume, where the laws of physics simply stop working. Time, as far as the equations go, ceases to exist at that singularity, and so the standard narrative says nothing came before because there was no before to begin with. But that answer has never felt quite satisfying. Not to everyone. It leaves us with a blank wall where our curiosity wants to go deeper. It also raises a strange contradiction. How can anything, even time, truly emerge from nothing? If time had a beginning, does that mean there was once a state of absolute timelessness? And if so, how could anything emerge from it, if nothing could change? After all, change requires time. For one thing to become another, a sequence has to occur, and if there was no time, how could anything start? Some scientists argue that the very idea of before the Big Bang might be meaningless, like asking what's north of the North Pole. Others suggest that we need a new way of thinking about time altogether, that time isn't a fixed arrow moving forward, but something more flexible, more emergent, like a property that appears only when the right ingredients come together. This line of thought has led to a growing field of pre-Big Bang models, alternative theories that imagine what might have existed before what we call the beginning. One of the most intriguing ideas is known as the Big Bounce. Rather than the universe springing into existence from nothing, the Big Bounce suggests that it was born from the collapse of a previous universe, that space and time didn't begin at the Big Bang. They simply passed through a transformation. Imagine a previous cosmos, expanding for billions of years, then slowly contracting, galaxies drawing closer, energy compressing, eventually reaching a critical density, and then rebounding, not into destruction, but into creation. The Big Bang, in this model, isn't a birth, it's a bounce, the echo of a cosmos collapsing and starting again. This idea is supported by some models of quantum gravity, especially one called loop quantum cosmology. In this framework, space and time are not continuous, but made up of tiny discrete loops, a bit like the pixels on a screen. And at very high energies, gravity becomes repulsive instead of attractive, which could allow the universe to avoid a singularity altogether. Instead of ending in a breakdown of physics, it might simply reverse course. Other models go even further, proposing not just one bounce, but endless cycles. In these cyclic universe theories, the cosmos undergoes a repeated pattern of expansion, collapse, and renewal. There is no beginning, no final end, only rhythm, eons upon eons of universes rising and falling, like a breath drawn slowly in and released again. One version of this idea comes from conformal cyclic cosmology, proposed by the mathematician Roger Penrose. He suggests that the incredibly distant future of one universe, when it has expanded so far and cooled so much that everything is smooth and uniform again, could actually serve as the beginning of another. In his model, time effectively resets, and the Big Bang of one universe is the quiet final whisper of the universe before it. Then there are other ideas, even stranger, that propose our universe might have emerged from a timeless state entirely. Not a prior universe or a cycle, but something like a quantum vacuum, a state of pure potential, where time and space don't yet exist but can arise spontaneously under the right conditions. In these models, the laws of quantum mechanics allow for fluctuations to occur even in this timeless void. A tiny bubble of spacetime could appear, not because something caused it, but because at a quantum level, even nothingness isn't truly empty. And from this bubble, a universe could form, one like ours, expanding, cooling, unfolding. The concept is difficult to visualize, and maybe that's the point. If time itself is not fundamental, if it's something that emerges from deeper laws we don't yet understand, then our everyday logic, shaped by clocks and calendars, might not be enough to grasp what came before. Still, the search continues, because whether the answer is a bounce, a cycle, or something far stranger, the question pulls us onward. It lingers not just at the edges of the cosmos, but at the edge of understanding itself. And just beyond that edge, more possibilities begin to stir. If we allow ourselves to imagine that the Big Bang wasn't truly the beginning, then we also have to consider what kind of event might have come before it. What kind of universe or pre-universe might have existed, and what forces could have brought about the birth of our own. This brings us to an idea known as the Big Bounce hypothesis. Instead of a universe that exploded into being from nothing, the Big Bounce suggests a very different possibility, that our universe was once part of a much older cosmos, one that expanded for billions of years, then slowly began to contract. Galaxies would have drifted closer, light would have grown hotter, space itself would have started folding inward, and eventually the entire universe would have reached a point of maximum compression, a moment of extreme density and energy. But rather than ending in a singularity, a place where the laws of physics break down completely, this model proposes something else. It suggests that as everything condensed into a tighter and tighter space, something unusual happened, gravity reversed, not in a magical or mysterious way, but through the lens of physics. At ultra-high densities, according to a framework called loop quantum cosmology, gravity may actually stop pulling things inward. Instead, it might push back, acting not as a force of attraction, but one of repulsion. To understand this, it helps to step away from the smooth, continuous version of space that we're used to. In classical physics, we think of space and time as seamless, like an infinite sheet that can bend and stretch without limit. But loop quantum cosmology takes a different approach. It suggests that space isn't smooth at all. Instead, it's made of tiny, discrete loops, unimaginably small bits of structure, far below the scale of atoms or particles. You can think of them like the pixels of reality, woven together into a flexible but granular fabric. and at extremely high energies, those loops begin to behave in new and unexpected ways. In this model, as the universe contracts and energy becomes concentrated, these loops reach a critical point. And instead of allowing the fabric of space to collapse into a singularity, they push outward, creating a bounce, a rebounding event that halts the collapse and begins a fresh expansion. Not an explosion, but a turning point, a new universe born from the collapse of the one before it. This concept offers a quiet elegance. It replaces the idea of an abrupt beginning with a rhythmic flow, a cycle of collapse and rebirth that might stretch endlessly in both directions. No starting line, no singular edge, just a bouncing cosmos, forever oscillating between expansion and contraction. But a beautiful idea is not enough. For the big bounce to be taken seriously, it needs support, clues, signs, or patterns in our own universe that might hint at what came before. And some researchers believe there may be hints hiding in the structure of the cosmos itself. One area of interest is the cosmic microwave background, the faint radiation that fills the universe and serves as a kind of afterglow from the early universe. Some scientists have proposed that subtle irregularities in this background, small asymmetries, cold spots, or circular patterns, might be evidence of a previous universe's collapse, imprinted like a fingerprint on the birth of our own. These ideas remain speculative, and not all cosmologists agree on how to interpret such patterns. But the possibility that we're seeing echoes from a past universe, faint ripples carried across the bounce, is one that continues to inspire research. There's also the question of entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy tends to increase over time. And yet, the early universe appears to have started in an incredibly low entropy state. That's something the standard Big Bang model doesn't easily explain. But a bounce coming after a long cycle of collapse could potentially reset the conditions, allowing a low entropy beginning to emerge naturally, without the need for special tuning. And then there's the behavior of black holes. Some theories suggest that as black holes collapse inward, they may create bridges to other universes or even birth new regions of space. While still highly theoretical, these ideas tie into the broader theme of rebirth through gravitational collapse, a core idea within bouncing cosmologies. The math behind these models is complex and the evidence is subtle, but the questions they raise and the possibilities they unlock stretch far beyond the boundaries of traditional cosmology. Because if the universe has bounced once, it might bounce again, and if it has bounced before, then perhaps we're not the first observers to witness a night sky filled with stars. Perhaps other civilizations, long gone, have also looked up and wondered about their place in a cosmos that breathes in and out across the ages. As our story continues, new theories begin to unfold, theories that stretch even further from our familiar physics, theories that imagine not just bouncing universes, but endless branches, infinite expansions, and a multiverse where every beginning is just one of many. If the idea of a bouncing universe opens the door to something before the Big Bang, then another idea pushes that door even wider, revealing a cosmic landscape far stranger than we might have ever imagined. It begins with inflation, the brief moment of rapid expansion we explored earlier, proposed to have happened just after the Big Bang. In most versions of that theory, inflation stops shortly after it begins. The universe inflates, smooths itself out, and then settles into the kind of expansion we see today. But in the 1980s, physicist Andre Linde suggested something different. What if inflation didn't stop everywhere at once? What if it continued eternally in some regions of space while stopping in others? This idea is known as eternal inflation, and it leads to a universe that looks very different from the one we picture in our minds. Instead of one single cosmos expanding from a single event, eternal inflation describes a vast, ever growing field of space, inflating forever. Within this inflating background, tiny pockets of space stop inflating here and there, like little bubbles freezing into place inside a boiling pot. Each one of those pockets becomes a universe, not a planet, not a star system, but an entire universe, with its own space, its own time, its own laws of physics. In this view, our universe, the one we live in, the one born from what we call the Big Bang, is just one of these bubbles, one pocket universe floating in an unimaginably vast multiverse, a single spark among an eternal storm of creation. It's an unsettling idea because it stretches our sense of scale beyond anything we're used to. We've already learned to accept that Earth is just one planet among many, orbiting one star among billions, inside one galaxy among trillions. But this suggests that even our entire universe may be just one small region in a much larger structure, a structure that never stops growing and never stops creating. In each of these pocket universes, the rules might be different. Some might have more dimensions, others might have different fundamental forces, or particles, or even timelines that flow in ways we can't understand. Some might be lifeless, others might be teeming with possibilities. And maybe, just maybe, a few might contain something that feels familiar. This multiverse isn't just a science fiction fantasy, it's a logical consequence of combining the mathematics of inflation with the uncertainty of quantum mechanics. Because quantum fields, like the one believed to have driven inflation, don't behave the same way in every place. They fluctuate, they bubble, they vary from region to region, and in a space that's inflating forever, those fluctuations have endless room to play. The result is a kind of cosmic patchwork, an eternal inflating background, constantly giving rise to new universes through random quantum variations. From a scientific point of view, this solves some big problems. It helps explain why our universe has the particular properties it does, why certain constants, like the strength of gravity or the charge of an electron, fall within such narrow ranges that life is even possible. In a multiverse, every possible variation exists somewhere, so the fact that we exist in a universe that happens to support life isn't a mystery, it's a selection effect. We see this universe because it's the one that lets us exist in the first place. But this idea also raises new questions. If there are infinite universes, each with different outcomes, then what does it mean for anything to be unique? Is our universe special, or just one page in an endless book? And then there's the question of evidence. How could we ever test such a theory? If these other universes are sealed off from us, their bubbles forever separated by inflating space, then their light can never reach us. We can't see them. We can't touch them. We can't even communicate with them. Some scientists argue that this makes the multiverse unscientific, an idea that can't be observed, measured, or falsified. Others believe that indirect clues might still be possible, tiny imprints left on the cosmic microwave background, or subtle signatures in the mathematics of quantum fields. Still, the deeper pull of this theory isn't just scientific, it's emotional, philosophical. It asks us to consider our place in something truly infinite, not just in size, but in possibility. A reality where every version of every outcome plays out somewhere, where every decision, every path, every history is written and rewritten, forever branching in directions we'll never see. And perhaps that's the most haunting part. That in some other universe, just like this one, another version of you is listening to this same story, drifting through the same ideas, falling asleep under the same stars, but in a sky governed by slightly different rules. As we float onward, we'll explore more of these strange possibilities, because in the world of cosmology, the more we discover, the more it seems the universe is not just bigger than we thought, but stranger than we can imagine. The idea that time flows in one direction, from past to present to future, is something we usually take for granted. It's built into our language, our clocks, and our very sense of existence. One moment follows another, never repeating, always moving forward. But some scientists have begun to imagine something different, not a straight line, but a cycle. One of those scientists is Roger Penrose, a Nobel Prize winning physicist known for his deep insights into the nature of space, time, and black holes. He proposed a theory called conformal cyclic cosmology, or CCC for short. In this model, the universe doesn't just begin and end, it repeats, not in the way a clock resets every 12 hours, but in a much stranger, deeper sense. According to Penrose, each universe has a life, a full timeline. It begins, it expands, it evolves, and it eventually fades. And when that fading reaches a certain point, the conditions become just right for something new to begin. Each of these full lifetimes, from Big Bang to final fade, is called an aeon, and our universe, Penrose suggests, is just one aeon in an infinite chain, a cycle of universes, one giving rise to the next, stretching endlessly forward and backward through time. But how could that be possible? If one universe dies, goes cold, empty, and still, how could another be born from that silence? The key lies in how time and space behave when stretched to their extremes. In our current universe, everything is expanding, galaxies are drifting apart, space is growing, and over the longest scales, this expansion appears to accelerate, driven by something we call dark energy. Left unchecked, this process will continue forever. Trillions of years from now, all the stars will burn out, black holes will evaporate, matter will decay, and eventually the universe will become a smooth, cold void, nothing but energy spread thin across an ever growing emptiness. At that point, something interesting happens. As the universe loses all its mass, time and distance begin to lose their meaning. Without matter to define scale, to mark sizes, shapes, or intervals, space itself becomes conformally invariant. That's a fancy way of saying the universe becomes scale free. In this strange condition, it no longer matters how big or small things are. Geometry flattens. Distinctions between vast and tiny dissolve. And when that happens, Penrose believes the far future of one universe becomes mathematically identical to the beginning of another, not because they're the same in size or structure, but because in this scale-free state, the geometry can be reinterpreted, stretched, reshaped, and used to define the next Big Bang. In this view, the Big Bang isn't the start of everything, it's a kind of continuation, the rebirth of structure and time from the infinite stillness of the aeon before it. Each new universe inherits the smooth, featureless calm of the one that came before. But not everything may be lost, because Penrose believes that black holes, those mysterious objects that swallow everything that falls into them, might act as messengers between aeons. Black holes, as we know, eventually evaporate through a process called Hawking radiation. Over unimaginable timescales, they lose mass and vanish. But what if they leave behind traces? What if the radiation they emit carries tiny patterns, imprints of the matter and energy they once consumed? Penrose suggests that these patterns could survive the end of one aeon and appear in the next. They wouldn't be obvious. They'd be incredibly subtle, perhaps faint spots or tiny ripples in the cosmic microwave background, but they might contain information, ghostly records of events that happened long before our universe ever began. And in recent years, Penrose and his collaborators have claimed to find hints of these patterns, specific circular shapes in the cosmic microwave background that they believe could be Hawking points from the aeon before ours. These claims are still controversial. Many scientists remain skeptical. The patterns could be statistical noise. The evidence is not yet strong enough to confirm, but the possibility that echoes of a previous universe are written into the sky above us is enough to stir the imagination. Because if Penrose is right, we are living in just one chapter of an endless story. A story made not of isolated universes, but of linked lives, each one fading into the next, leaving behind only the softest clues. And this idea offers a different kind of infinity, not the sprawling, disconnected multiverse of eternal inflation, where anything and everything happens somewhere, but a single thread, infinite in length, yet shaped by continuity, one universe giving rise to another, again and again, across an endless chain of time. Each aeon contains its own galaxies, its own physics, its own mysteries, but they are all connected, quietly, elegantly, perhaps even purposefully. And if the future of our universe is already becoming the beginning of the next, then time is not a river flowing in one direction, it is a circle. As we drift further into the possible origins of our universe, the questions grow stranger, and the answers begin to shimmer with ideas that stretch the imagination to its edge. So far, we've imagined bouncing universes, eternal inflations, and cosmic cycles. But there's another path, one that doesn't begin with space and time as we know them at all, but instead with something far smaller, far more fundamental: strings. In the world of classical physics, particles are imagined as tiny points, zero-dimensional objects like mathematical dots that have mass and charge but no size. But string theory changes that image entirely. Instead of points, it imagines that the smallest building blocks of the universe are tiny vibrating strings, loops, or segments so small they make atoms look gigantic by comparison. Each string vibrates at its own frequency, like a note on an instrument, and the vibration determines what kind of particle it is: an electron, a photon, or something else entirely. In this picture, everything in the universe, all matter and forces, are simply different notes played on the same cosmic string. But these strings don't just vibrate in the three dimensions of space that we experience: length, width, and height, and one of time. They need more room to move. According to string theory, the universe isn't four-dimensional, but 10-dimensional, or in some versions, 11. Most of these extra dimensions are hidden. They're not stretched out like the space we move through, but curled up tightly, so small and compact that we can't see them even with our most sensitive tools. They exist at the tiniest scales, woven into the very fabric of reality, quietly shaping the properties of particles and forces. But if dimensions beyond our perception are real, they may also hold the key to what came before the Big Bang. String theory evolved into something broader, an even more ambitious framework known as M theory. In M theory, strings are not the only basic elements. There are also higher dimensional objects called branes, short for membranes. A brane can be one-dimensional, like a string, or two-dimensional, like a surface, or three-dimensional, like the space we live in. And here's where the idea becomes breathtaking. M theory suggests that our entire universe, everything we know, could be a three-dimensional brane floating inside a higher dimensional space. All of our galaxies, stars, atoms, and even time itself could exist on this brane, while other branes float alongside us, separated by dimensions we cannot see. According to one proposal, the Big Bang wasn't the beginning of space and time, but the result of a collision between two of these branes. Picture two vast, flexible sheets in a higher dimensional space, drifting slowly toward each other. When they collide, the energy released could ignite a new universe. Not a universe from nothing, but from the impact of structures that already existed in a higher dimensional realm. This event wouldn't be an explosion in a pre-existing space, but the birth of a universe as space and time unfold from the collision. The brains would bounce apart again, possibly to drift for trillions of years before crashing once more, starting the process all over again. And in this model, our universe is just one pocket or region where such a collision happened. There could be other brains, other universes, all existing in the same higher dimensional space, but cut off from each other, like pages in a book that never touch. Each brain might follow its own laws of physics. Some might have more dimensions, some fewer. Some might contain stars and galaxies, while others remain empty or evolve in ways we can't even imagine. In this way, M theory gives rise to its own kind of multiverse, a cosmos made not just of many regions, but of many realities, stacked and spread across invisible dimensions. But what makes this idea so powerful is that it doesn't rely on speculation alone. It arises from the mathematical demands of string theory, from the way the equations only work in higher dimensions, from the way different types of particles emerge, and from the need to unify gravity with quantum mechanics. For decades, scientists have searched for a theory of everything, a framework that brings together the large-scale structure of the cosmos, described by general relativity, with the tiny world of particles and forces, described by quantum field theory. String theory and its extension through M theory is one of the most promising attempts, and although we haven't yet found direct evidence of strings or brains, many physicists believe that they offer the most elegant blueprint for what reality might truly be made of, including what may have existed before the Big Bang. Perhaps our universe wasn't born alone. Perhaps it didn't begin in isolation. Perhaps it emerged from the crash of cosmic membranes drifting through a space beyond space, a realm of unseen dimensions where the deepest notes of creation still echo, far beyond what our eyes can see. And if this is true, then our story is part of something far larger, not just in space, but in the very nature of what it means to exist. As our journey through the possible origins of the universe continues, we begin to see a pattern forming, not of beginnings from nothing, but of transformations, of one state becoming another, of old structures giving rise to new ones. And in this spirit, we arrive at a model that blends the mystery of higher dimensions with the logic of cause and effect. It's called the ekpyrotic universe model, a name drawn from the ancient Greek word ekpyrosis, which means conflagration or cosmic fire. In this model, the universe wasn't born from a singularity, not from an infinitely dense point where the laws of physics break down, but from a collision, a violent but meaningful event between two vast three-dimensional structures known as brains. And just like in M theory and string theory, the ekpyrotic model imagines that our universe exists on a brain, a kind of three-dimensional sheet floating in a higher dimensional space. But here, there's another brain nearby, parallel to ours, invisible, untouchable, and yet intimately connected through a larger, unseen dimension. For an unthinkably long time, these two brains drift closer, slowly, silently. As they approach, the energy between them builds, until finally they collide. But unlike ordinary objects crashing into one another, these brains are not made of atoms or particles. They're made of space itself. So when they touch, they don't smash, they ignite. The collision doesn't destroy the brains. Instead, it triggers the release of an immense wave of energy, enough to heat up the space on our brain and give birth to all the matter, radiation, and structure we now see in the universe. In this story, the Big Bang is not the beginning of everything. It's not a singular origin point. It's the aftermath of a cosmic impact, the spark that lit up our region of space and set time flowing in the direction we now experience. This model carries a quiet elegance. It offers a way to avoid the troubling idea of a singularity, where the math of general relativity breaks down and we're left with unanswered questions. Instead of a breakdown, it gives us a transition, one shaped by geometry, motion, and hidden dimensions. But the ekpyrotic model doesn't stop with a single collision. In many versions, the brains don't just meet once, they rebound, and over time, they drift apart again, only to be drawn back together once more. This leads to a cyclic cosmology, where the universe undergoes repeated cycles of contraction, collision, expansion, and cooling. No beginning, no final end, just a pattern that stretches across eternity. Each collision would look, from the inside, like a big bang. Each expansion would produce galaxies and stars. Each cooling period would lead to stillness until the next bounce begins again. This idea is comforting in a way. It paints a picture of a universe that is not a fragile accident, but a recurring process, something stable, rhythmical, and vast beyond imagining. But like all bold theories, the ekpyrotic model is not without challenges. One of the strengths of this approach is that it offers answers to some of the same problems inflation was designed to fix, like the horizon problem and the flatness of the universe. By allowing the universe to begin in a highly ordered cold state before the collision, the model avoids the need for inflation altogether. It also gives a reason for why our universe appears to be three-dimensional. If the brains themselves are three-dimensional objects, then everything born from their interaction would also be three-dimensional, including space as we experience it. But critics have raised concerns. Some scientists argue that the math behind the brain collision is still incomplete, that it's not yet clear how such a collision would unfold in full detail, or how the energy would transfer smoothly into particles and fields without creating inconsistencies. Others point out that while the theory avoids a singularity, it introduces its own puzzles. For example, what sets the timing of the cycles? Why do the brains drift together and apart in just the right way? What keeps the pattern going, and could it break? There's also the question of evidence. While the model makes some testable predictions, such as certain patterns in the cosmic microwave background or specific distributions of primordial gravitational waves, so far, these predictions remain difficult to confirm with current technology. And like many ideas that deal with dimensions beyond our own, parts of the ekpyrotic model may always be hidden from direct observation, just outside the reach of our instruments, like shadows on the wall of a much larger room. Still, the idea that we live in the aftermath of a collision, not a singularity, reshapes how we think about beginnings. It invites us to imagine a cosmos filled with structure before our universe existed, and to see the Big Bang not as a lone spark from nowhere, but as part of a much larger dance, one that may still be unfolding just beyond the edge of space. And as our exploration deepens, we'll soon meet other theories, some based on quantum foam, some on gravity's breakdown, and others that challenge whether space and time even need to exist at all. Because the further back we go, the more the line between physics and mystery begins to blur, and the more the story begins to open, not with a bang, but with possibility. As we drift even closer to the edge of the beginning, beyond bounces, beyond brains, beyond bubbles of inflating space, we arrive at a place where even space itself begins to dissolve, not in the sense of disappearing, but in the sense of no longer being solid or smooth or continuous. At the very tiniest scales imaginable, reality begins to shimmer, it breaks apart, it dances. This is the realm of the quantum foam. To reach this scale, we have to zoom in farther than atoms, farther than protons and electrons, down to a length known as the Planck length, a distance so small that if a single atom were the size of the entire solar system, the Planck length would still be far smaller than a speck of dust. At this level, space is not a calm, steady stage on which events unfold. Instead, it seethes with activity. Particles pop in and out of existence. Energy flickers randomly. Space itself begins to warp and twist in unpredictable ways. It's not a smooth surface, it's a foamy chaos, bubbling with uncertainty. That's why physicist John Wheeler, who first imagined this strange layer of reality, gave it the name quantum foam. And here in this bubbling mess, some physicists believe lies the answer to how the universe could have emerged without needing anything to come before it. Because according to the rules of quantum mechanics, the vacuum, what we normally think of as nothing, is never truly empty. It's filled with potential, with fluctuations, with fields that can momentarily rise and fall, like tiny waves in a dark ocean. Every so often, one of these fluctuations might become large enough to give rise to something stable, a bubble of space, a pocket of order, a universe. This is the idea of quantum fluctuation, that the universe itself might have originated not from a pre existing thing, not from a collapse, and not from a collision, but from the random, restless activity of quantum fields. That something like our universe could have emerged from nothing, simply because even nothing is unstable at the smallest scales. But this raises a deeper question. If space itself is part of the foam, part of what emerges, then maybe space and time are not fundamental at all. Maybe they're not the backdrop of the universe, but part of the performance. This is where modern physics begins to shift from viewing space and time as the stage to viewing them as actors in the play. In recent years, a growing number of scientists have explored the idea that space time is emergent, that it's not a basic ingredient of reality, but something that forms from deeper, more abstract structures, like a pattern emerging from threads or a melody emerging from vibrations. Some models suggest that space-time might emerge from quantum entanglement, the mysterious connection between particles that allows them to influence each other instantly, no matter how far apart they are. This phenomenon, which Einstein once called spooky action at a distance, may actually be the glue that holds space itself together. In these models, space is not continuous. It's made of connections, networks, relationships. The distances we measure might not be properties of space, but side effects of how quantum bits or qubits are entangled. And gravity, the force that curves space and holds planets in orbit, might not be fundamental either. It might emerge naturally from the way these quantum relationships arrange themselves. Just as heat emerges from the random motion of atoms, gravity might emerge from the collective behavior of quantum information. This idea is subtle and strange. It turns the universe inside out. It suggests that what we experience, space, time, geometry, motion, might all be illusions, not false, but emergent, secondary, and that what's truly real lies deeper, beneath the foam, beneath the ripples, beneath even the idea of place. If this is true, then the beginning of the universe wasn't a moment in time or a point in space. It was the birth of space and time themselves, a transition from a timeless, formless quantum state into the structured, expanding cosmos we now inhabit. There would be no before, no outside, just a shift, like a wave forming on a still pond, that created not only matter and energy, but the very canvas on which those things could exist. In this picture, the Big Bang wasn't the origin of stuff. It was the origin of the arena, an arena that may be nothing more than the large-scale echo of entangled particles woven together into something that only looks like space. And as we drift through these ideas, past dimensions, past bouncing universes, past collisions of cosmic sheets, we find ourselves not just questioning how the universe began, but questioning what it even means to begin. Because at the edge of quantum reality, the questions grow quiet, and the answers, perhaps, are not out there in space, but deep within the structure of thought itself. The deeper we go into the mystery of our universe's beginning, the more it feels like we're circling a shadow, something hidden, powerful, and deeply strange. And perhaps no object in the cosmos captures that feeling quite like a black hole. From the outside, black holes look deceptively simple. They're invisible spheres in space, with gravity so strong that nothing, not even light, can escape once it falls inside. But what happens on the inside? That's a question even our best physics still can't fully answer. At the center of a black hole, we believe there's something called a singularity, a point where all the mass collapses into infinite density, and where the fabric of space-time becomes so warped that our current understanding breaks down completely. It's a mystery, and strangely, it's the same kind of mystery we encounter when we try to rewind the universe all the way back to the Big Bang, where time, space, and matter compress into a singular origin point that defies explanation. That similarity has led some physicists to ask a bold question. What if the universe itself is the inside of a black hole? It sounds strange, but the idea is rooted in a curious kind of symmetry. When a massive star collapses and forms a black hole, its interior becomes sealed off from the rest of the universe by the event horizon, a boundary that hides whatever happens inside. To an outside observer, time appears to freeze at the horizon. What lies within is beyond reach. But from the inside, things keep going, space keeps stretching, time keeps moving forward. It becomes its own private world, curved inward, expanding like a bubble, hidden from the rest of existence. Some theorists suggest that this hidden interior might not end in destruction, but in creation, that the singularity inside a black hole might not just collapse endlessly, but bounce rebounding on the other side of some physical threshold and giving rise to something new. A sudden expansion, a burst of energy and space, a baby universe budding off from the parent cosmos. And if this is possible for a black hole, could it also be true for our own universe? Could the Big Bang itself be the exit of a black hole that formed in a higher dimensional space? This is where the idea of white holes enters the picture. A white hole is the theoretical opposite of a black hole. Instead of pulling everything in, it pushes everything out. Nothing can enter a white hole, but matter and energy can stream out as if ejected from somewhere else. While black holes are formed by collapse, white holes are described as explosive events. They erupt, they expand, and they release matter that seems to come from nowhere. We've never observed a white hole in the sky, but some scientists believe they may exist, not as long-lived objects, but as brief events. And some even wonder if the Big Bang itself was a kind of white hole moment. The sudden outpouring of space, time, and matter, all spilling out from a boundary we can't see. In this view, the Big Bang wasn't a singularity of beginning, it was the end of something else. The inside of a collapsed region that became unstable and burst open on the other side. The physics behind these ideas is deeply connected to general relativity and quantum gravity, two fields that still don't fully agree. In relativity, black holes are smooth, predictable, and eternal, but in quantum theory, nothing is ever truly permanent. Even black holes can evaporate, even space can fluctuate, and in this uncertain zone between theories, new ideas begin to form. Some researchers propose that as a black hole collapses, it reaches a point of quantum resistance, a limit where gravity is countered by the chaotic push of quantum effects. Instead of forming a permanent singularity, the core rebounds and expands on the other side. In some models, this expansion can create a new universe with its own dimensions and physical laws. It might be completely disconnected from its parent, unreachable, undetectable, a separate branch in the tree of existence. And that brings us to a fascinating possibility that every black hole might be a seed of a new universe, that each collapse in our cosmos could give birth to a cosmos of its own, like bubbles inside bubbles, a recursive universe where every death is also a creation. In this framework, the Big Bang becomes not a one time explosion, but a link in a much larger chain, the visible edge of a process that stretches back beyond space, beyond time, and maybe beyond our own universe. It also raises deeper philosophical questions. If black holes can give rise to new universes, could our universe have inherited certain properties, not randomly, but through natural selection? Could the conditions that make black holes more likely to form also shape the birth of more universes, favoring universes like ours? It's an idea known as cosmological natural selection, where the laws of physics evolve across generations of universes, each born inside the black holes of the last. We don't yet know if this is true. We don't know if black holes really lead anywhere at all. But they remain one of the most mysterious and powerful features of the cosmos, places where time warps, space folds, and the very idea of a beginning might be redefined. And as we continue toward the deepest corners of scientific theory, the fabric of the universe becomes thinner and the questions become quieter, because what lies on the other side of a black hole might just be the place where everything we know was born. Among all the mysteries of the universe, one of the quietest and yet most powerful is the mystery of entropy. It's a concept that lives in the world of thermodynamics, the science of heat, energy, and disorder. But it touches everything from how stars burn out, to how time moves forward, to how the universe itself may have begun. Entropy, at its simplest, is a measure of disorder. It describes how spread out energy is, how mixed together things have become. A hot cup of tea, when left on the table, cools down. Its heat spreads into the air. Its molecules slow down. Its energy becomes less useful. That's entropy at work. And entropy has a rule: it always increases. This rule is known as the second law of thermodynamics. Over time, systems tend to become more disordered, more uniform, more mixed. A tidy room, left alone, gets messy. A drop of ink spilled in water doesn't unspill. The world naturally moves from order to disorder, from structure to randomness. But entropy does more than govern heat and mess. It gives us the thing we often take most for granted: the arrow of time. In physics, most fundamental laws are symmetric. They don't care whether time flows forward or backward. Equations work both ways, but in reality, we only ever move in one direction, forward. We remember the past, not the future. We age, not reverse. Stars form, then fade. The cosmos expands but does not contract. This forward flow, the sense of time moving in a single direction, comes from entropy. As disorder increases, time flows with it, not because clocks tick, but because the universe is constantly drifting toward more probable states. There are more ways for things to be disordered than for them to be ordered, so over time, disorder wins. But here's the strange part: if entropy always increases, then the universe must have started in a very low entropy state, a state of high order, high concentration, and low randomness. The earliest universe, small, hot, and dense, must have been incredibly well organized for entropy to have had so much room to grow. And that's a puzzle, because low entropy states are rare, they're statistically unlikely, they don't just happen by chance, not without something preparing them. So if the Big Bang began in a low entropy condition, what caused that? Why would the universe start so strangely organized? Some scientists suggest that this unusual starting point isn't a coincidence at all, but a clue, a whisper from before the beginning, a thermodynamic fingerprint left behind by whatever came before. One idea is that the early low entropy universe wasn't a start, but a rebound. That entropy in a prior cosmos had built up during a long phase of collapse, that as a previous universe shrank and cooled, its disorder peaked and then reset. This brings us to cyclic cosmologies, models where the universe doesn't begin and end, but loops. Universes expanding, collapsing, bouncing again and again. In these models, entropy might increase in each cycle, but be redistributed in ways we don't fully understand. Some versions imagine entropy being pushed into extra dimensions or diluted across time. Others suggest that the entropy of one universe could help prepare the low entropy start of the next, but the challenge is real. In a truly cyclic model, entropy would build up more and more with each cycle, eventually making future universes too disordered to form structure at all. So, to make this idea work, something would need to counteract that accumulation, a mechanism to erase or recycle entropy. This idea remains one of the great questions in theoretical physics. Can entropy be reset? And if so, how? Some thinkers propose that gravity plays a unique role here, that the early universe's smoothness was deceptive. While uniform energy may seem disordered, gravity prefers clumps, stars, galaxies, black holes. So, in a sense, the early universe was actually very ordered under the influence of gravity because it had not yet formed those clumps. From that view, the Big Bang wasn't just hot and dense, it was also smooth. And smoothness in gravitational terms is a special low entropy condition. As the universe evolved, gravity began pulling matter together, forming complexity and increasing entropy. There are also speculative ideas involving the Weyl curvature hypothesis proposed by Roger Penrose. In this picture, the beginning of the universe was smooth, not just in density, but in its geometry, a condition where the curvature of space was simple and uniform. This special start might have set the stage for time to begin flowing, for entropy to start increasing, and for structure to eventually form. All of this suggests that entropy, this quiet, relentless force, is not just about heat or decay, it's about history, about how we got here, about the structure and memory of the universe itself. And wherever the universe came from, a bounce, a cycle, a fluctuation, or a collision, it had to begin in a way that allowed time to begin flowing and entropy to begin rising, because without entropy, there would be no clocks, no stars, no breath, and perhaps no story to tell at all. Long after the fires of the Big Bang had cooled, after the first atoms formed and the universe went dark, something ancient remained, a faint, whispering glow, still traveling through space. This glow is called the cosmic microwave background, or CMB for short. It is not light in the way we usually think of it, not like sunlight or a star's shimmer. It's a soft, invisible microwave signal stretched thin across the entire sky. And yet it is among the most important clues we have about the origin of everything. Discovered in 1965 by Arno Penzias and Robert Wilson, who were actually looking for something else. The CMB turned out to be a leftover echo of the Big Bang, the afterglow of a universe once hot, dense, and glowing, now cooled to just a few degrees above absolute zero. At first glance, the CMB appears almost perfectly uniform. No matter where we look in the sky, the temperature is astonishingly consistent, about 2.7 Kelvin. This smoothness once helped reinforce the Big Bang model. It showed that the early universe was incredibly uniform, with only tiny fluctuations that would eventually seed galaxies. But the more precisely we looked, the more strange details began to appear. Satellites like COBE, then WMAP, and more recently Planck gave us high-resolution maps of the CMB, and those maps revealed anomalies, oddities that didn't quite fit the standard picture. Subtle ripples, unexpected patterns, curious cold regions that stubbornly refused to align with the expected randomness. One of the most talked about features is a chilling mystery known as the cold spot. It's a large region of the sky, much colder than its surroundings. Not by a lot, just a fraction of a degree, but colder than it should be based on standard Big Bang expectations. It spans an area hundreds of times larger than our moon and appears to defy the uniformity that the Big Bang model predicts. Some cosmologists initially thought it could be explained by something called a supervoid, a vast, underdense region of space with fewer galaxies and less matter, which could stretch the CMB photons traveling through it, making them lose energy and appear cooler. But when astronomers looked, the evidence for such a void wasn't strong enough to explain it, and so the mystery remained. Others began asking bolder questions. Could this cold spot be more than just a statistical fluke? Could it be a bruise left behind by something from before the Big Bang? One idea, still deeply debated, is that the cold spot could be an imprint from a previous universe, a mark left over from an earlier cosmic cycle, or even a scar from a collision with another bubble universe, in a vast multiverse landscape where many Big Bangs may have occurred side by side. It's not just the cold spot that puzzles scientists. Other anomalies have emerged too, strange alignments that seem to stretch across opposite sides of the sky. Some call it the axis of evil, a dramatic name for a peculiar orientation in the temperature fluctuations of the CMB that seems to point in one particular direction. According to the standard model, the fluctuations in the CMB should be random, no preferred direction, no cosmic compass. But this axis, if real, hints at something larger and more structured than we expected. It's as though the early universe was tilted or shaped by something beyond our horizon. There are also unexpected hemispheric asymmetries. One half of the sky appears to have slightly more variation than the other. Again, the differences are small, but in cosmology, even small deviations can carry enormous meaning. The Planck satellite, launched by the European Space Agency in 2009, provided the most detailed map of the CMB yet. Its data confirmed the earlier findings from WMAP and brought even more precision, but it didn't erase the anomalies. If anything, it made them harder to ignore. Planck's data showed us that the universe's large-scale structure, while mostly aligned with predictions, had lingering oddities that couldn't be easily smoothed away. Scientists double-checked their instruments. They analyzed foreground dust. They modeled every possible source of interference. Still, the patterns remained, and that opens a deep and unsettling possibility. If these features are real, not artifacts, not mistakes, not random, then they could be evidence of something before the Big Bang, a pre-inflationary universe, a cosmic predecessor, a memory written in microwave light. Of course, it's still possible that these anomalies are nothing more than statistical noise. With only one universe to observe, it's hard to say what's truly unusual. We don't have a sample size of many cosmoses, just one, ours. Still, the questions linger. Why this cold spot? Why this axis? Why these slight imbalances in a universe that's supposed to be uniform? If we listen carefully to the CMB, this ancient hum from the dawn of time, it may be whispering more than just how the universe began. It might be trying to tell us what came before. And as we continue to map the sky, probe deeper into these fluctuations, and build more sensitive instruments, we may one day learn whether these echoes are the random static of chance or the faint fingerprints of something much older than the Big Bang itself. As we stare into the deep fabric of the cosmos, past the galaxies, the clusters, the glow of the ancient microwave background, we encounter a quiet but profound surprise. The universe is expanding. That much has been known since the early 20th century, when Edwin Hubble discovered that distant galaxies are moving away from us, and the farther they are, the faster they recede. This redshift, as it's called, was our first real clue that the universe wasn't static. At first, scientists believed the expansion might be slowing down, as though cosmic gravity, like an invisible hand, was gently tugging everything back. After all, with all the matter in the universe, stars, gas, galaxies, and even dark matter, surely gravity would put up a fight. But in 1998, two teams of astronomers studying distant exploding stars called Type 1a supernovae found something astonishing. These dying stars acted like cosmic beacons, their brightness telling us how far away they were and how fast the universe had stretched since their light first left them. What the teams found didn't make sense at first. Instead of slowing down, the universe was speeding up. The expansion wasn't being restrained by gravity, it was accelerating, as if some mysterious pressure spread thinly across the cosmos was pushing everything apart faster and faster. This force became known as dark energy. We call it dark not because it's spooky or invisible, but because we don't know what it is. It doesn't emit light. It doesn't clump like matter. It doesn't behave like anything we've seen in physics. And yet, according to the latest data, it makes up about 68% of everything in the universe. More than galaxies, more than dark matter, more than all the atoms in every star, every planet, and every breath of air. Dark energy is everywhere, even here, in the room where you're listening, but it's incredibly diffuse. A teaspoonful of dark energy wouldn't weigh anything noticeable. Its effects only show up on the largest scales, across cosmic distances, in the grand stretching of space itself. The simplest explanation for dark energy is something called the cosmological constant, an idea that Einstein himself proposed, then abandoned, then was posthumously vindicated for. The cosmological constant suggests that empty space has energy, that even in the absence of particles, light, or matter, space isn't truly empty. It has a kind of built-in pressure, a property of space-time itself, and that pressure pushes outward. But other scientists think dark energy might not be constant at all. Instead, it could be dynamic, evolving over time. Some models suggest a mysterious field called quintessence that slowly changes its behavior as the universe expands. Others propose a complete revision of gravity itself, that perhaps our theory of how space-time bends and warps isn't quite right on the largest scales. These ideas are still speculative, but the implications run deep, because if dark energy is real, and all signs point to yes, then it doesn't just affect how the universe expands, it touches how it began and how it might end. If dark energy was present in the early universe, and if it behaved differently back then, it could alter our understanding of the Big Bang itself. Some theorists wonder whether it played a role not just in speeding up the cosmos now, but in shaping the inflationary burst that supposedly happened in the very first slivers of a second. Or maybe, just maybe, dark energy hints at a deeper layer of reality, a framework beneath space-time, beneath matter and force, where what we call energy and space are simply different faces of the same underlying structure. We don't yet know what that structure is, but dark energy might be its echo. Looking ahead, the influence of dark energy shapes our predictions about the universe's future. If the expansion continues to accelerate, galaxies will grow more and more distant, the night sky will thin out. Over unimaginable stretches of time, stars will burn out, galaxies will drift beyond our view, and even light will become scarce. This fate is called the heat death, a slow, cold unraveling of all structure and energy. But if dark energy grows stronger over time, not constant, but intensifying, we might face an even stranger fate, the Big Rip. In that scenario, not only galaxies and stars would be torn apart, but eventually atoms, molecules, even space-time itself. The universe would shred from the inside out. On the other hand, if dark energy fades or changes direction, the expansion might one day reverse. Galaxies would slow, then drift back together. Gravity would take the lead, and the universe would collapse into itself, a big crunch that could set the stage for another beginning, perhaps even a bounce. For now, we don't know which path we're on. The story of dark energy is still being written. Telescopes like the James Webb Space Telescope and upcoming missions like Euclid and the Nancy Grace Roman Space Telescope are searching for new clues, faint signals in ancient light that might reveal whether dark energy is constant or changing. We listen closely, watching galaxies drift like quiet leaves on a stretching pond, measuring every flicker, every shift, searching for patterns in the pull of deep time. And though we don't yet know what dark energy truly is, its quiet push is the silent heartbeat of the cosmos. As we continue drifting deeper into the universe's most elusive mysteries, we arrive at another puzzle, one that surrounds us entirely, yet remains invisible. It's called dark matter, and like dark energy, its name is simply a placeholder, a quiet admission that we don't yet know what it truly is. But unlike dark energy, which pushes the universe apart, dark matter pulls things together. It behaves like gravity's hidden scaffolding, the unseen framework holding galaxies in place. When astronomers observe galaxies spinning, they notice something strange. The stars at the edges are moving far too fast. According to Newton's and Einstein's laws, those stars should be flung away like leaves from a spinning fan. But they're not. They hold together. Something invisible is keeping them from drifting off into space. The same mystery shows up when scientists look at galaxy clusters, vast collections of galaxies bound together by gravity. The visible matter we can see, all the stars, gas, dust, doesn't provide nearly enough gravity to explain the speed and behavior of these systems, yet they hold together anyway. The only explanation that seems to fit is this: there's a hidden form of matter, something we can't see, can't touch, and can't shine a light on, but it's there, acting like glue, silently shaping the cosmos. Dark matter is believed to make up around 27% of the universe, far more than ordinary matter, which makes up just 5%. That means everything we've ever seen, every star, planet, person, and particle, is just a small sliver of what actually exists. The rest is dark, unseen, waiting. For decades, scientists have tried to catch it in the act. In underground laboratories, they've built sensitive detectors, shielded by mountains, hoping to catch a glimpse of a dark matter particle bumping into a regular one. Telescopes scan the heavens for clues. Supercomputers simulate cosmic evolution under its influence. But so far, nothing. We know it's there from the way it bends light around galaxies, from how it shapes the early patterns of the cosmic microwave background, from its gravitational fingerprints all across the universe. But we can't see it. We don't know what it's made of. And that's opened the door to even deeper questions. What if dark matter isn't just a modern mystery, but a primordial one? Could it be older than the Big Bang itself? Some scientists are exploring the idea that dark matter could be a relic from a previous universe, a leftover trace of physics from before time began, or before our universe took its current form. If the cosmos went through a bounce or a cycle, or emerged from some higher dimensional brain interaction, it's possible that dark matter is a fossil of that earlier reality. It might not obey the same rules as ordinary matter, because it wasn't born in the same moment. And if that's true, then dark matter isn't just part of our universe. It might be a clue to what came before it. Other ideas reach for simplicity, suggesting that maybe we don't need a new particle at all. Maybe, just maybe, our understanding of gravity is incomplete. These ideas fall under a category called modified gravity theories, with names like known as modified Newtonian dynamics, and T-Vase. Instead of adding an invisible substance to the universe, they tweak the laws of motion. These models suggest that gravity behaves differently at very large distances or very low accelerations, meaning we might only think we need dark matter, when, in fact, gravity is just more flexible than we realized. But these alternative theories face challenges. They can explain the rotation of galaxies, yes, but struggle to match the full range of observations, especially on cosmic scales like the behavior of galaxy clusters or the large scale structure of the universe. They often require patching or exceptions, and without a solid theoretical foundation linking them to known physics, they remain intriguing but incomplete. Meanwhile, dark matter, as mysterious as it is, continues to fit the data. It continues to hold galaxies together in computer simulations. It continues to be the best explanation we have for the cosmic web, the vast filamentary structure connecting galaxy clusters across billions of light years. It continues to quietly shape the evolution of the universe. Some researchers now look toward axions, ultralight particles that may act like a field, humming gently across space. Others investigate WIMPs, weakly interacting massive particles, long favored but so far undetected. Some theories imagine an entire dark sector, a shadow universe made of particles and forces that we haven't discovered yet, interacting with our own only through gravity. And still, despite all our effort, no one has yet caught one. It's as if the universe is whispering a secret, gently, patiently, and just out of reach. We can feel dark matter's presence. We see its influence, but it remains a ghost, a cosmic question mark wrapped around every galaxy, every star, every step we take. What is it made of? Where did it come from? And could it be a bridge between the universe we know and the one that came before it? And now we drift into something even stranger than matter or space. We enter the mystery of time, the quiet current that carries everything forward, yet refuses to be touched. We live inside time. We measure our lives by it. Seconds, minutes, hours, days that turn into decades. We speak of the past as something behind us. The future is something ahead. Time feels like an arrow, always flying forward, never backward. But what is it, really? And more curiously, did time begin? The Big Bang is often described as the beginning of time. But if we imagine a before, the whole idea starts to tremble. How can there be a before if time didn't exist yet? What does it even mean to ask what came before the first tick of the cosmic clock? It's a question that bends the mind and even the laws of physics. Some physicists argue that time is not fundamental at all. It might not be a basic ingredient of reality like matter or energy. Instead, it could be something that emerges, like a ripple on a pond, a byproduct of deeper processes that aren't tied to clocks or calendars. One of those deeper processes may be quantum entanglement. When particles become entangled, they act as one, no matter how far apart they are. Their properties are linked. Some researchers believe that the structure of space-time itself, including time, could emerge from the complex web of entanglement between particles. That time may not be a backdrop at all, but a side effect of how particles interact. Others point to thermodynamics, the science of heat and energy. In that world, time is closely tied to entropy, the idea that systems naturally become more disordered over time. A hot cup of tea cools down, a sandcastle collapses, a dropped glass shatters, and never unshatters. This forward motion, this irreversibility, is how we experience time. Not because time is pushing forward, but because entropy is increasing. In a universe with no entropy, could time even be said to flow? Could the arrow of time be nothing more than a reflection of our perspective, shaped by the second law of thermodynamics? There are even physicists who believe that the universe, at its deepest level, might be timeless, that the equations describing quantum gravity, those attempts to unite Einstein's curved spacetime with the jittery world of quantum particles don't include time as a variable at all. The math just doesn't need it. One such idea comes from a framework called the Wheeler-DeWitt equation. It describes the quantum state of the entire universe, but if you read it carefully, there's something strange. No time variable. It treats the universe as a whole, a frozen, timeless block. Everything that has ever happened or will happen laid out in one giant, unchanging picture. To us, this feels alien. Life feels like a flowing story, not a static photograph. But perhaps our experience of time, of change, of memory is something created within the block, not by the block itself. And so the idea arises, maybe time isn't real in the way we think it is. But then the next question becomes even more haunting. If there was no time, how did anything begin? If time is an illusion, what does beginning even mean? This is where the language of physics begins to break down, and where imagination must take its place. Some theorists imagine that what we call the beginning was not a sharp line or a sudden event, but more like a transition, a shift from one state of being to another, not in time, but across something deeper, something more abstract. Perhaps our universe emerged from a timeless quantum field, a restless, fluctuating sea of potential. From this sea, a patch of energy collapsed into order, forming space and time as we know them. In this view, time unfolded with the universe, like a wave curling forward from stillness, not a bang, but a blossom. And in certain models, especially those rooted in quantum gravity, time might not even be universal, it could be local. In different regions of space, or under different conditions, time could behave differently, or not exist at all. Just as temperature can vary, so too might time. The universe could be stitched together from patches of different clock zones, a cosmic quilt rather than a single ticking watch. So when we ask what happened before the Big Bang, we may be chasing a shadow, asking a question that assumes time exists where it doesn't. And yet, our hearts resist this because we remember, we hope, we age, we dream of tomorrows. Time feels real because we feel it. Even if physics tells us it's an illusion, it's the illusion we live in. But maybe, just maybe, that illusion is trying to tell us something, that what we call the beginning may not be a beginning at all, that we might be part of something far stranger, far deeper, and far older than time itself. If time can bend, pause, or even disappear from our deepest equations, then we must wonder what happens to space, and more strangely, what happens to us. In our everyday experience, the universe flows like a river. We paddle forward through the current of time, never backward, with only memories behind us and guesses ahead. But some physicists suggest this flow is just a feeling, that reality doesn't actually move. Instead, imagine that everything, every heartbeat, every flash of light, every star being born, and every tear being shed is already there, fixed, eternal, laid out like a cosmic book where every page exists at once. This is the idea of the block universe. In this model, space and time form a single four-dimensional shape, often called spacetime, and inside this spacetime block, the past, the present, and the future all exist simultaneously, not as separate stages, but as slices of one vast, unchanging whole. It's like looking at a loaf of bread, where each slice represents a moment. Our lives feel like we're moving from slice to slice, but in reality, the entire loaf is already baked from the first slice to the last. In this view, you as a baby still exist. So does you tomorrow. So does every version of every person who ever lived, all frozen in their respective slices of spacetime. Every laugh, every breath, every goodbye, not gone, not waiting, just there. And if that's true, then what becomes of the idea of a beginning? Can we even talk about something starting when everything already is? It's a question that pulls at the fabric of how we understand existence. In the block universe, the Big Bang doesn't erupt forward in time. Instead, it sits at one end of the loaf, not as a starting line, but as one of many frames in the full picture. It's not a bang that led to now, but simply a region in the block, no more special than your 10th birthday, the fall of Rome, or a star forming 10 billion years from now. This changes everything. It means time, as we experience it, may just be a mental bookmark, flipping through the pages of a story that's already written. Our minds process events in order, giving us the illusion of movement, of cause and effect, of yesterday becoming today. But the block doesn't care about sequence. To it, all events are equal, all points in time are places. In this picture, the flow of time, the ticking of seconds, isn't something the universe does. It's something we perceive, like the way a still photo can seem to breathe if you stare at it long enough. The block universe suggests that our perception of change may be no more real than the sensation of speed when you're sitting in a stationary train and another one moves beside you. But how does this model arise? It flows naturally from Einstein's theory of relativity. In that theory, time doesn't tick at the same rate for everyone. A clock on a spaceship ticks differently than a clock on Earth. What one person sees as now may be another person's later. This flexibility of time leads to a strange conclusion. If time can be rearranged based on motion, then all moments must already exist. Otherwise, what are we rearranging? Relativity, then, doesn't just allow the block universe, it quietly demands it. Still, it's one thing to accept the math and another to live inside the idea. Because if everything already exists, do we really have free will? Are we just puppets dancing along a pre written path? It's a haunting thought, and yet some find comfort in it. Because if time is an illusion, then nothing is truly lost. That warm summer day, that final goodbye, that first smile, they're still there. They haven't vanished. They simply live in another corner of the block, forever etched into the geometry of existence. And if that's true, then maybe we're never truly alone. Maybe the people we miss, the moments we long for, aren't gone, just elsewhere. Still real, still there. But this idea also raises deeper questions. If we can no longer speak of becoming, only of being, what does that mean for a universe that we once thought began? Is the Big Bang just the outer shell of something larger, not a beginning, but a boundary? And if the block exists as a whole, who or what shaped it? Or did it shape itself, needing no cause, because cause itself only makes sense within the illusion of time? As we drift deeper into the silence between seconds, we begin to understand just how much of reality might lie beyond our senses, beyond motion, beyond memory, because in the stillness of the block, everything already is. If we keep peeling back the layers of the universe, removing galaxies, stars, atoms, particles, eventually we're left with a haunting question. What's left when there's nothing left? Is there such a thing as nothing? It seems like a simple idea. Nothing is nothing. An empty room, a blank page, a silence so deep it hums. But the closer we look, the more slippery the concept becomes. Because even in a completely empty room, there's still air, still light bouncing, still gravity pressing. Strip all that away, no air, no walls, no particles, not even a single photon, and you still have space, a place for nothing to be. But space isn't truly empty either. According to quantum physics, even the deepest vacuum is full of activity. Tiny particles blink in and out of existence, like fireflies flickering inside a jar you can't open. These are called quantum fluctuations. They arise not from something, but from the structure of reality itself. In fact, it's these fluctuations that scientists believe helped shape the earliest moments of our universe. Little ripples in the vacuum, stretched out by cosmic inflation, may have become the seeds of galaxies. In this way, nothing gave rise to everything. So, what does that say about the very beginning? If we ask what came before the Big Bang, or before time, or before space, we're often told nothing. But that word doesn't behave like we expect. It carries the weight of philosophy, mathematics, and physics, but resists definition in all of them. The ancient Greeks wrestled with this problem too. The philosopher Parmenides claimed that nothing could not exist, because the moment you try to think about it, you're already thinking of something. To speak of nothing is to give it a form, which means it's no longer nothing. On the other hand, Democritus, who first proposed atoms, believed in the void, an empty space through which particles move, a true nothingness without matter where existence plays out like a dance in the dark. These two visions, one denying the possibility of nothing, the other building a universe from it, echo through every modern debate about the cosmos. In mathematics, zero is a powerful concept. It holds place, it balances equations, but zero is not nothing. It's a symbol, a number, a measurable absence, but it still is. In physics, we've tried to create the most perfect vacuum possible, chambers where atoms are sucked away, electromagnetic fields are canceled, and temperatures fall close to absolute zero. But even there, tiny energies persist. The so called 0 point energy, the lowest possible energy a system can have, still hums in the darkness, still does something. It turns out the universe doesn't like true nothingness. It resists it, fights it, or maybe it simply can't be it. Even a complete void, when modeled by physicists, still has laws, still obeys symmetries, still allows for the existence of fields, constants, and dimensions. The fabric of reality doesn't unravel into non being. It warps, shifts, or hides, but it never disappears completely. So maybe the more helpful question isn't, what is nothing? Maybe it's, can something ever not be? If nothing cannot exist without some kind of structure, then it may not be the absence of everything, but the hidden state of potential, a stillness waiting to become motion, a silence waiting to sing. In this view, nothing is not a void, it's a cradle, a place where existence rests before awakening, a canvas, not blank, but stretched and primed for color, not zero, but zeroed, waiting. And if that's true, then maybe our universe didn't emerge from nothing, but through it, as if nothingness was a membrane, a thin veil we pass through on our way to becoming. Some thinkers go further. They suggest that reality itself may be inevitable, that once certain rules exist, like logic or math, existence must follow, that nothing can only remain nothing if nothing is even allowed to exist. But if possibility exists, then so must something. It's a dizzying thought that the universe doesn't need a cause, because nothingness was never a viable option. And that means that even before there was something, there may have already been the possibility of something, which is, in a way, something. So when we ask what is nothing, we might be asking the wrong question, because in the language of the cosmos, maybe nothing is just the pause between notes, the breath before the word, the hush between heartbeats, a space that feels empty but holds the blueprint for everything that will ever be. What if the universe didn't come from something but simply emerged, on its own, from a sea of nothingness that wasn't truly nothing at all? That's the daring idea proposed by theoretical physicist Lawrence Krauss in his provocative concept, a universe from nothing. At first, it sounds like sleight of hand, a trick, a word game. How can something, time, space, galaxies, matter, light, just appear from nothing? But Krauss's version of nothing isn't an empty void or a blank black canvas. In quantum physics, nothing isn't truly empty. It's more like a restless, frothy field, a quantum vacuum, where particles constantly flicker in and out of existence, like fireflies appearing for a blink and then vanishing again. These are called virtual particles. They aren't stable or permanent, but they exist briefly in the strange rules of quantum uncertainty. One moment, they're not there. The next, they are, and then they're gone again, always borrowing energy from the vacuum and then paying it back just as fast. This strange dance happens all the time, all around us, even in the emptiest parts of space. In fact, these flickers are so real that they can push against metal plates placed very close together, a phenomenon called the Casimir effect, something pushing from what we once thought was nothing. Now imagine that, in this ever simmering quantum vacuum, a fluctuation occurs, a rare, massive one, a tiny bubble of space that inflates, expands, and cools, and keeps growing. That bubble, according to Krauss and others, could be the birth of a universe, our universe. In this model, the laws of physics don't need anything before. They don't need a creator or a trigger or even time as we know it. They just allow a spontaneous natural emergence because the rules of quantum mechanics say that anything not forbidden must happen eventually. And that includes the appearance of something, even from apparent emptiness. And here's where it gets even stranger. According to quantum field theory, even empty space contains a kind of energy called vacuum energy. It's the energy of the fields that fill space, even when there are no particles present. And it's not zero. In fact, it might even be responsible for the universe's accelerating expansion, the same mystery we call dark energy. If space has energy and quantum fields can fluctuate, then maybe the conditions for a universe to appear aren't so rare after all. Maybe they're inevitable. In Krauss's picture, the total energy of the universe might even be zero. Matter, stars, galaxies all have positive energy, but gravity, the force that pulls things together, contributes negative energy. And in a strange twist of cosmic accounting, these might cancel out. The positive and the negative could balance perfectly, which means the net energy of the entire universe could be exactly zero. If that's true, then maybe it didn't cost anything to make a universe. Maybe it didn't require anything at all. Just a fluctuation, just the rules, and enough time. But here's where language starts to blur again, because this nothing, this quantum vacuum, isn't truly nothing. It's governed by laws. It allows for fluctuation, structure, emergence. It contains the seeds of space, time, and possibility. It's more like a primordial quantum soup, silent, invisible, but full of hidden potential. And that opens up new questions. If every nothing still holds the possibility of something, was there ever such a thing as true nothing? Was the vacuum itself always there? Or did the laws that allow fluctuations somehow arise from nothing too? Even in this elegant theory, where a universe can emerge without a trigger, we're left wondering, what are the laws made of? Where do they live? Who or what wrote the rules? Krauss would say they simply are, that they don't require explanation beyond themselves, that existence doesn't need a why, only a how. But others find that answer too thin, too quiet. They want to know what lies beneath the laws, beneath the fields, beneath even the vacuum. Still, there's something deeply poetic about the idea that our vast universe, filled with stars and dreams and laughter, might be the result of a tiny silent twitch in the fabric of a quantum fog. That everything we are, every planet, every breath, every thought, could have emerged from a shimmer in the darkness, not because it was planned, but because it could, and that, in the end, might be enough. What if everything, from the stars in the sky to the thoughts in your mind, isn't quite as solid or real as it seems? What if the entire universe is a simulation, It sounds like science fiction, a plot twist from a movie. But surprisingly, some scientists and philosophers take the idea seriously, not because they think we're all trapped inside a giant video game, but because modern physics, mathematics, and logic are starting to whisper the same strange possibility that the universe may not be what it appears. One version of this idea comes from philosopher Nick Bostrom, who proposed that if civilizations survive long enough to develop powerful computers, powerful enough to simulate conscious beings and entire worlds, then it's possible that simulated universes would vastly outnumber real ones. And if that's true, how would we know if we're in a simulation or not? But there's also a more physics based approach to this question. And it's even stranger because when we look at the deepest level of reality, down to quantum fields and black hole boundaries, we start to see signs that the universe may behave less like a giant object and more like a calculation, a kind of cosmic code. This brings us to one of the most fascinating concepts in theoretical physics, the holographic principle. At its heart, the holographic principle suggests that everything we experience in three dimensions, space, time, gravity, matter, might actually be encoded on a distant two-dimensional surface, like a hologram. In a hologram, a flat surface contains all the information needed to create the illusion of depth. You move your head, and the image seems to shift in 3D space, but it's all coming from a 2D pattern. What if our entire universe is like that? This idea began with a puzzle about black holes. According to Stephen Hawking, black holes have entropy, a measure of information, and it turns out that the amount of information they can store is not based on their volume, but on the surface area of their event horizon. This was deeply strange. We're used to thinking of storage or content as something that fills up space, but black holes seem to suggest that information is stored on the boundary, not in the center. Physicists Gerard 't Hooft and Leonard Susskind took this further. They proposed that maybe the entire universe works this way, that all the information about everything we see, every planet, every tree, every memory, might be stored on a distant cosmic boundary, like the walls of a faraway shell, and everything we experience here, in three dimensions, is just a projection of that data, not a lesser reality, but a different kind. A reality where space, gravity, and even time might emerge from deeper, more abstract information. In this picture, the Big Bang may not have been an actual explosion or expansion of stuff, but a shift in how that underlying information was arranged, like a sudden change in code that produced the illusion of a universe expanding in time. Some theories suggest that what we perceive as the beginning, the Big Bang, could be more like a rendering event, the moment the projection began, not the birth of reality, but the moment it became visible to conscious observers like us. And just like in a computer simulation, the question what came before may not make sense. There may be no before. The system might have booted up, and that's all. What's even more curious is that some string theories, especially in versions like ADDS/FT correspondence, give mathematical evidence for holography. In these models, gravity in a 3D world is equivalent to quantum physics without gravity in 2D, two completely different pictures describing the same universe. If true, this could be one of the most radical shifts in understanding since Galileo pointed a telescope to the sky. It would mean that reality isn't what we touch or see, but something deeper, more abstract, woven from data, probability, and structure, and it challenges everything about the Big Bang, because in a holographic or simulated universe, the idea of a fiery beginning may just be a visible artifact of deeper rules. The bang might not have been a birth, but a launch, and what launched it may be code, mathematical laws, embedded instructions, a framework that doesn't need a past, just a process, and that raises haunting questions. If the universe is a hologram, where's the surface it's projected from? If it's a simulation, who or what is running it? And if time and space are illusions created by computation, does anything really begin or end at all? As we drift into these ideas, we begin to realize that the border between science and philosophy, between physics and mystery, grows thinner and thinner, and the next step on our journey takes us to the very nature of information itself. Long before telescopes scanned the skies, before equations described the stars, and even before the word universe had a name, human beings looked up and wondered. They saw the night sky as a canvas of mystery, not empty, but alive, full of meaning, full of motion. And as they tried to make sense of it, ancient cultures gave birth to some of the most beautiful and imaginative ideas about where everything came from. One of the oldest and most widespread is the image of the cosmic egg. In Hindu cosmology, it's called Hirani Garbha, the golden womb, or golden egg, a radiant sphere that floated in endless darkness, and from it all of creation was born. It cracked open, and space poured out. Time began, gods emerged, and the world, as we know it, came into being. In ancient Greek myths, too, the world begins from a cosmic egg. Out of the egg hatches Phanes, the first god of light, who then sets the universe in motion. Then there's the idea of primordial chaos, not chaos as in wild disorder, but as in pure potential. In ancient Egyptian mythology, there was Nun, the dark, endless ocean of nothingness. From its waters rose the first mound of land, and on it the god Atum created life. A similar story appears in Mesopotamian myth. The world begins not with a bang, but with the taming of chaos, a dragon-like ocean goddess named Tiamat, whose body is carved into the heavens and the earth. In Norse mythology, before anything else existed, there was Ginnungagap, a vast yawning void between realms of fire and ice. And when those two realms touched, the heat and the frost met, and life began to stir. Then there are stories of cycles, not just one creation, but many. In some Mayan beliefs, we are living in the fifth world, the fifth version of reality, after four others were destroyed. The Aztecs told similar stories of suns that rose and fell, worlds that began and ended. Even in ancient China, the philosopher Zhuangzi described a universe that flows like breath, expanding and contracting endlessly, with no absolute beginning or end. At first glance, these myths feel poetic, metaphorical, symbolic, but what's curious is that many of their ideas echo in today's deepest scientific models. The cosmic egg, a sealed origin point, expanding outward, doesn't sound so different from our own modern idea of a hot, dense origin. The image of cycles, of worlds rising and falling, collapses giving way to rebirth, echoes in bounce cosmologies and conformal cyclic theories. And the idea of chaos, pure, formless potential, feels not far off from quantum fluctuations in a vacuum, a kind of modern-day sea of possibility, waiting to give birth to something real. Of course, ancient people didn't have particle accelerators or deep space observatories. They didn't know about redshift or background radiation, but they had something else. They had intuition. They had story. They watched the tides, the moon, the rising and setting of stars. They noticed that everything in life comes in waves: birth, growth, decay, death, and perhaps rebirth. And so instead of straight lines, their cosmologies were often circular. Instead of an absolute beginning, they imagined motion, transformation, return, not nothing becoming something, but something changing shape, which raises a strange and quiet question. What if science and mythology are not opposites, but distant cousins? What if the metaphors we once used to make sense of the sky, the eggs, the dragons, the cycles, the breaths, or poetic reflections of truths too big to measure. Even today, scientists must use metaphors. We talk about space-time stretching, like fabric. We call waves ripples, even though space has no water. We say particles interact, like they're little people with intentions. In a way, modern cosmology is just another story, a carefully tested, mathematically precise story, but a story nonetheless. One that still tries to explain where we came from, why things are the way they are, and whether there was ever truly a beginning. And when science hits its limits, when math becomes silence, and logic starts to fold in on itself, sometimes the old stories whisper again. Maybe the universe began as a breath. Maybe it's one of many. Maybe it cracked open like a shell, or flowed out of the stillness, or pulsed like a beating heart. As we drift between physics and philosophy, between equations and intuition, one thing becomes clear. We've always wondered. We still wonder. And maybe that wondering is the universe learning to look back at itself. Somewhere in the soft glow of moonlight, or perhaps in the quiet hum of thought just before sleep, there lies a strange and gentle puzzle, one that bends the rules of what we thought we knew. It begins not with galaxies or dark matter, but with something far smaller, something so small, in fact, it seems to slip through our grasp the moment we try to look at it. Quantum mechanics, the science of the tiniest pieces of reality, has never played by ordinary rules. It asks us to imagine particles that act like waves, waves that collapse into points, particles that can be in more than one place at once, until we decide to look. At the heart of this mystery is something called the observer effect, the idea that just by watching, we might be changing what's there, not by touching it or interfering with it in any obvious way, but simply by being aware of it. Take the famous double slit experiment. Fire tiny particles like electrons or photons through two narrow slits. If no one's watching which slit they pass through, the particles behave like waves, creating a strange interference pattern, as though each one went through both slits at the same time. But if we observe them, if we place even the smallest detector to watch the path, suddenly they snap into behaving like particles. The interference vanishes. The very act of observing changes the outcome, but it doesn't stop there. Physicists began to wonder, what if you only decide to observe after the particle has already passed through the slits? Enter the delayed choice experiment, imagined by physicist John Wheeler. In this experiment, a particle is sent toward the slits, and only after it has presumably chosen a path do we randomly decide whether to measure which path it took or let it interfere like a wave. The shocking result? The outcome still depends on the observer's choice, even if that choice happens after the particle should have made its decision. It's as if reality waits to be told what it was and doesn't settle into a definite past until we ask. This leads to something called retrocausality, the idea that causes and effects can move backward in time, that a future measurement might influence a past event. Not in a science fiction time-traveling sort of way, but in a quiet mathematical whisper that ripples backward through the probabilities. So what does this have to do with the universe? It leads us to a deeper and more unsettling question. If reality isn't fully real until it's observed, what about the biggest event of all? What about the Big Bang? We often imagine the Big Bang as something that happened long ago, once and for all, a single spark, lighting the universe into being. But if quantum mechanics teaches us that observation can influence outcomes and even reshape past events, could it be that our act of observing the universe now is affecting how we understand its beginning? When we look into deep space, we're also looking back in time. The light from distant galaxies has traveled billions of years to reach us, and the further we look, the closer we get to the Big Bang itself. But here's the twist, the cosmic microwave background. The faint glow from the early universe only becomes real to us when we measure it. It wasn't glowing in our direction all along, waiting for us to see it. In quantum terms, it didn't fully exist until it became part of our observation. Some physicists have even suggested that the Big Bang, or at least the way we perceive it, might be observer dependent, that our very existence as conscious beings, capable of asking, measuring, and wondering, might be shaping the way the universe unfolds its story to us. It's not that we created the Big Bang, but rather our observations today may be entangled with the earliest conditions of the cosmos. The quantum field that underlies everything is not a fixed stage where events happen independently. Instead, it's more like a web, dynamic, responsive, and curiously aware of the questions we ask. This doesn't mean we can control reality, but it might mean that reality isn't truly complete until it is observed. And so, as strange as it sounds, the universe might not have had a fixed objective beginning. Instead, it may have always contained a shimmering cloud of possibilities, and it's only through our present day measurements, telescopes, and equations that those possibilities collapse into the version we now call the past, a past that appears solid, a past that appears ancient, but one that, in the quantum realm, is still softly echoing with the choices of the present. Somewhere between the silence of numbers and the soft hum of the cosmos lies a radical idea, one that doesn't start with atoms or particles, one that begins not with fire or matter, but with mathematics. The Swedish American physicist Max Tegmark once proposed something that at first sounds more like a dream than a theory. He called it the mathematical universe hypothesis. But its most expansive version, level 4, doesn't stop at just one universe. It opens the door to every universe, all of them, all at once. It starts with a quiet, curious question. What is the universe, really? Is it made of stuff, particles, and energy that swirl and collide to form galaxies and stars? Or is it made of something more abstract, a kind of logical scaffolding, built not from substance, but from pure relations and quantities? Tegmark's bold answer is this: the universe is not just described by math. It is math, not a metaphor, not a convenient tool, but the real underlying fabric of reality. In this view, every structure that can exist mathematically, every consistent equation, every logically sound geometry, every internally coherent set of rules describes a real universe, and we are simply living in one of them. Not the only one, not even necessarily the most special one, just one mathematical structure among an infinite sea of possibilities, a structure that happens to allow beings like us to emerge and ask questions. This is what Tegmark called level 4 of the multiverse, a realm where every conceivable mathematical universe exists, whether or not it resembles ours. Some might have different physical constants, some might have more or fewer dimensions, some might not contain space or time at all. Others might exist as pure number systems, never giving rise to anything like matter or life. But they all exist in the same way the number pi exists, not because someone wrote it down, but because it simply must be. And just as the digits of pi go on forever, revealing endless patterns and surprises, so too might these mathematical universes stretch out, limitless and untouched. So what does this mean for the Big Bang? In this framework, the Big Bang, that fiery beginning we've spent so much time exploring, might not be a singular defining moment. It might just be one feature of one particular solution to a particular set of mathematical equations. Our universe's birth could be as mundane in this context as a ripple in a pond or the crest of a wave, a consequence of starting conditions within one math-based reality. And it may be that the only reason we experience this version of a universe with galaxies, atoms, and the arrow of time is because this mathematical structure supports conscious observers. In other words, We live in a universe that can be understood because we're the kind of beings who can understand. This idea is closely tied to something called the anthropic principle, the notion that the universe must have properties that allow observers to exist, simply because otherwise there would be no one here to observe it. It doesn't mean the universe was made for us, only that we find ourselves in a universe that permits minds to evolve, because only those kinds of universes can ever be questioned. And out of the infinite possibilities, it is only in certain structured, rule abiding frameworks where questions like what came before the Big Bang can even arise. But this raises a strange thought. If all mathematical structures exist, if every universe that can exist does exist, then what is the role of randomness? What is the role of causality, of purpose? In this level 4 multiverse, there may be no deeper why. There is only the logic of numbers, the structure of systems, the elegance of equations, playing out in ways both chaotic and calm. It's as if reality is not so much created as discovered. And we, like curious explorers waking up inside a cathedral of geometry, are only just beginning to notice the carvings on the walls. In some versions of this theory, the Big Bang doesn't matter at all. The entire universe, its past, present, and future, is simply there in the math, static, eternal. Not a story with a beginning, but a shape that exists beyond time. And from this view, existence itself feels less like a loud explosion and more like the silent proof of a beautiful theorem, an existence not born, not caused, but simply required by the rules of logic. And somewhere inside this grand structure, this infinite library of mathematical realities, is us, not accidental, not central, just compatible. A solution to an equation we do not yet fully understand, but one that we are living, breathing, and slowly deciphering, one gentle question at a time. Must everything have a beginning? It's a question that feels built into us, woven into the fabric of how we think. We imagine stories starting with a first sentence, rivers flowing from a source, lives beginning with a first breath. And when we look out at the universe, we naturally ask, when did it begin? But what if that question is based on a false assumption? What if the universe didn't begin at all? Not in an explosion, not from a previous cycle, not as the result of some deeper cause, but simply is eternal, infinite, uncaused. It's a concept that sits uneasily with the human mind. We're trained to look for causes, for triggers. Every effect must have a cause. Every event must come from something. But the idea of something without a beginning, without a cause, feels like trying to balance on a beam that extends forever in both directions. There's no edge to grip, no starting point to measure from. And yet, not everything we observe fits neatly into our expectations, especially when it comes to the cosmos. Some physicists have suggested that perhaps the universe never needed a beginning in the first place, that it didn't explode into existence, but has simply been here, always, changing, evolving, stretching, and flowing, but never starting, never ending. This brings us back to an idea once considered revolutionary and later largely discarded, known as the steady state model. First proposed in the mid 20th century by scientists like Fred Hoyle, Thomas Gold, and Hermann Bondi, the steady state theory claimed that the universe has no beginning or end. As galaxies move apart due to expansion, new matter is continuously created to fill in the gaps, keeping the average density of the universe constant over time. From this perspective, the universe always looks roughly the same on a large scale, no matter when or where you look. It's a universe without a birth certificate, a cosmos that doesn't age in the way we expect, one that has always existed and always will, in a grand, unchanging rhythm of creation and dispersal. The steady state model was elegant, simple, even comforting in its timelessness. But eventually, observations began to paint a different picture. The discovery of the cosmic microwave background radiation in the 1960s provided strong evidence for a hot, dense early universe, something the steady state model couldn't explain. As more data poured in, the Big Bang theory took its place as the dominant explanation for the origin of everything. And yet, the core idea behind the steady state model, the notion that the universe may not have had a beginning, has never fully disappeared. It lingers in the background of cosmology, whispering possibilities into newer models and modified frameworks. In some reimagined versions, the universe is not steady in its structure, but still eternal in its timeline. Instead of new matter being created continuously, perhaps the universe goes through slow transformations, expanding, cooling, changing in form, but never coming from nothing, never needing a singularity, just always there. This idea often ties into the concept of an infinite universe, one that stretches endlessly in all directions, with no edges, no boundaries, no central origin. In such a cosmos, asking where or when it began may be like asking where the surface of a sphere starts. There is no privileged point, no beginning, just continuity. And if it has no edge in space, why must it have an edge in time? Some theories suggest that the laws of physics might allow for such an infinite, uncaused universe, that instead of being sparked into being, reality exists as a kind of self sustaining loop, a system that doesn't rely on external input to operate. Like a mathematical truth, it just is. Others go further, imagining a cosmos where time itself is not linear but circular, where moments recur in endless loops, or where cause and effect blur together in a self contained structure that never requires a first cause. In this view, the universe might be compared to a flame, not started by a match, but existing as long as the conditions allow. Fuel, oxygen, and heat, all present, all interacting. The flame burns not because something lit it, but because it sustains itself. And so maybe the cosmos, too, is a kind of eternal fire, not ignited, not born, just blazing gently in the fabric of reality. Of course, these ideas challenge our intuition. They defy the comfort of a clear beginning, or dissolve the idea of a neat origin story. But the universe has never promised to make us comfortable. It only offers what is: vastness, wonder, mystery, and perhaps in the end, asking where it all began is like asking where a circle begins. You can point to any spot, but the truth is, the circle has no beginning and no end. It simply goes on. At some point in every scientific journey, you reach a boundary, a place where the maps end, where the equations grow uncertain, and our most trusted ideas begin to fray at the edges. That boundary for cosmology is unimaginably small, a fraction of a fraction of a second after what we call the Big Bang. It's known as Planck time, roughly 10^4 of bead seconds after the beginning, a moment so early, so compressed, and so energetic that our current laws of physics simply stop working. To understand why, we need to talk about the two great pillars of modern physics and why they don't like sharing the same room. On one side, we have general relativity, Einstein's sweeping description of how gravity curves space and time. It works beautifully on large scales: stars, galaxies, the expansion of the universe. On the other, we have quantum mechanics, the strange and jittery rules that govern the tiniest things: atoms, particles, and fields. Individually, they're spectacular. Together, they clash, especially in extreme environments like black holes or the very early universe. That's because the closer we rewind time toward the moment of the Big Bang, the more those two theories are forced to confront each other. At the Planck scale, the smallest unit of space and time we can meaningfully define, gravity is no longer weak and gentle. It becomes wild, chaotic, and unpredictable, just like the quantum world. And here's the problem: we don't yet have a quantum theory of gravity, a single framework that unites the immense with the minuscule, the smooth curves of space time with the frantic dance of particles. So when we try to model what happened before Planck time, before 10^4 seconds, our math breaks. The equations produce infinities. The concepts lose meaning. Time itself may stop behaving like time. Space may unravel into something unrecognizable. Or perhaps both simply vanish. That doesn't mean there's nothing there. It means we just don't know. We've hit the edge of scientific knowledge, not because we lack curiosity, but because our current tools, both theoretical and experimental, aren't powerful enough yet. Think of it like trying to read the first page of a burnt book. You see the middle chapters. The end makes some sense, but that opening, that spark that set it all in motion, is singed and missing, and even the words we'd use to describe it might not apply anymore. For example, when scientists try to simulate the early universe on a computer, the closer they get to the Big Bang, the more the simulations turn into noise. Past a certain threshold, even our most powerful supercomputers can't make sense of the inputs. And while space telescopes can peer far into the cosmic past, even close to the formation of the first galaxies, they can't see past the cosmic microwave background. That's the universe's baby picture. But behind it, behind that glowing wall of light, the data goes dark. The early moments are cloaked, not by secrecy, but by physics itself. And so we turn to theory. We build models, we speculate with discipline, we test what we can, rule out what doesn't fit, and keep adjusting. Ideas like string theory, loop quantum gravity, bounce cosmologies, and emergent spacetime try to bridge the gap. They offer glimpses of what might lie beyond, but none are complete. Not yet. There's a beautiful honesty in that. Because science isn't about pretending to know everything. It's about mapping the boundary between what we know and what we don't, and then gently pushing that boundary outward. It's in that frontier between certainty and mystery where wonder lives. And wonder isn't quiet here. It hums in the background of every question we ask. What existed before the Big Bang, if that concept even makes sense? Did time emerge from something deeper? Is the universe part of something larger, grander, even more unfathomable? We don't have those answers, not yet. But every particle accelerator we build, every cosmic signal we detect, every new theory we imagine takes us one step closer, because the story of the universe isn't finished. It's still unfolding. And maybe, just maybe, so is the science that will help us understand where it all began, or whether it began at all. We've looked outward into galaxies and inward toward quantum realms. We've wandered through brain collisions, cyclic aeons, inflationary multiverses, and the soft tremble of quantum foam. We've questioned space, time, matter, even the idea of beginnings. But now, as we stand at the edge of every idea ever formed, a quieter question begins to rise. What if there is no answer? Not because we haven't tried hard enough, not because we're asking the wrong questions, but because the answer might not be something the human brain was ever built to understand. It's a strange thought, unsettling at first. We like solutions, conclusions, theories that wrap up clean and neat. The universe began here, with this event, on this timeline. End of story. But the cosmos doesn't owe us simplicity. And maybe, just maybe, the origin of everything is something deeper than logic, wider than math, older than even the idea of before. In science, we often imagine that with the right tools, the right telescope, the right particle collider, we could eventually uncover all the truths. We trust in the slow, steady march of discovery. But what if this particular mystery is more like a horizon? No matter how far we walk toward it, it keeps moving just out of reach because we are human, and our minds, remarkable as they are, evolved not to decipher infinity, but to survive on a small blue planet, to find patterns in seasons, safety and shelter, warmth and connection. We carry the instincts of hunters and gatherers. We measure time by sunrises, trust what we can touch, and navigate the world using ideas that feel solid and familiar. But the beginning of the universe, that's not solid, it's not familiar. It may not even fit into the categories of before and after, and so we reach, and sometimes the silence that greets us isn't failure, it's a kind of awe. Philosophers have long warned that the human mind may only ever grasp reality through shadows and reflections, like echoes in a cave. We see hints, shapes, clues, but the whole, the real source of it all, maybe that's something we can only feel, not solve. That doesn't make the journey pointless. In fact, it may be the most beautiful part of being alive, that we wonder at all, that we dream up theories, not just to win prizes or prove equations, but to make sense of this deep, quiet question inside us. Where did everything come from? And why is there something rather than nothing? Sometimes the most profound truths are not answers, but the courage to live without one, to sit quietly with the unknown, to let it be vast and dark and magnificent without rushing to explain it away. Children often ask questions adults no longer ask, not because children are naive, but because they're still unafraid of not knowing. What if we allowed ourselves that same openness? What if the purpose of asking how the universe began wasn't to close the book, but to keep reading? Because even without a final answer, every theory we've explored, every bouncing cosmos, every stretched dimension, every simulated horizon has done something powerful. It has expanded our imagination. It has taught us that mystery is not the opposite of science. It is its lifeblood, that curiosity is a light we carry, not to banish the dark, but to dance with it, to find beauty in the shadows, to let the unanswered questions breathe. And maybe that's enough. Maybe the universe, in all its complexity, doesn't need to be solved like a puzzle, but sung like a song, felt like a whisper, or followed like a story with no final page. So we continue, not because we expect certainty, but because the mystery itself is sacred, and because lying here together under stars born from some ancient unknown, it's okay to wonder, it's okay to not know, and it's more than okay to be at peace with that. In the quiet that follows a great question, in that pause between what we think we know and what we still wonder, something magical begins to happen. Doubt, not fear, not failure, but the soft, powerful doubt that says, what if we're missing something? What if we looked at this another way? What if everything we believe is just the beginning? It's easy to think of science as a book of answers, sealed, settled, full of facts and formulas. But science, at its heart, is not a fortress of certainty. It's a garden of curiosity. Every breakthrough we celebrate, every orbit calculated, every element discovered, every cell, star, or subatomic particle understood, was born from someone who dared to question what came before. The greatest scientists weren't just experts, they were dreamers with discipline. They were people who looked at the same sky, the same numbers, the same stubborn problem, and asked a new question. Albert Einstein once said, "The important thing is not to stop questioning. That gentle insistence to keep asking is what turned a patent clerk into a man who reshaped our understanding of time and space." And long before Einstein, it was doubt that drove Galileo to lift his telescope toward the heavens and realize that Earth was not the center of everything. It was a question that sent Darwin wandering into the wilderness of biology. It was wonder, not certainty, that pulled Newton beneath the apple tree and into the laws of motion, and it still happens today. Every time a scientist says, that doesn't quite add up, or what if there's more to this story, the frontier of knowledge moves forward. This is the beauty of science. It doesn't fear being wrong. In fact, being wrong is part of the process, because when a model fails, it shows us where to look next. It reveals the cracks in the wall, the spaces where light can enter. The Big Bang itself wasn't a belief. It was a model built on observations, the expansion of galaxies, the afterglow of radiation, the uniformity of the sky. But even now, as we've seen, scientists continue to test it, question it, stretch it, not because they want to tear it down, but because they want to see how far the truth might go. Science is a moving thing, a living story, one that rewrites its chapters as the data evolves, one that knows it will never be finished. And so we embrace models, not as permanent truths, but as stepping stones. The Earth was once flat, then it was the center of the universe, then it was a blue marble spinning in a solar system, then a planet surrounded by invisible fields and wrapped in carbon and chaos. Each version held some truth and some limitation, but it was the willingness to ask, what if this isn't the whole picture, that made progress possible? And that same spirit continues in the search for how the universe began. Whether we're exploring bouncing universes, entangled dimensions, or foamy quantum chaos, it's the ability to hold competing ideas in our minds without clinging too tightly to any one of them that makes this journey so extraordinary. Because science doesn't always deal in answers, often it offers better questions, questions that open new doors, questions that link disciplines together, like physics and philosophy, astronomy and art, mathematics and mystery. And when those questions don't have clear answers, science doesn't retreat. It leans closer. It builds new instruments, retools old theories, and trains the next generation to keep listening. Because at the heart of it all is a deep humility, the quiet knowing that the universe is vast and we are just beginning to understand it. It's not weakness to admit we don't know, it's strength to keep searching anyway. The history of science is a history of changed minds, of brave admissions. We were wrong, but now we see something new. It's not about winning arguments, it's about discovering beauty in numbers, in patterns, in the way galaxies swirl, and atoms hum, and silence becomes something to study. So the next time we find ourselves overwhelmed by mystery, uncertain about what's real, or how it all fits together, we can take comfort in the fact that we're not alone. We're part of a long tradition of thinkers and seekers, stargazers and skeptics, who turned their doubts into telescopes and used them to look farther than anyone before. And just beyond that horizon, the next mystery is already waiting. For all the math and models, the graphs and gravitational equations, there's something deeply human at the heart of this cosmic search. Because when we ask where the universe came from, what we're really asking is what that means for us. A beginning isn't just a scientific point on a timeline. It's a mirror, one that reflects how we see ourselves. If the universe exploded into being from nothing, then perhaps everything, even life, even love, is the lucky result of a grand, chaotic accident. If it has always existed, stretching endlessly through time, then maybe we are a flicker of awareness in a timeless dream. If reality is one of many, a bubble in an infinite foam of universes, then what makes ours special? And if this is all a projection, a hologram, or a simulation, what does it mean to be real? These are not just questions of science, they are questions of identity and purpose. Because our origin stories, the ones we hold in the quiet corners of our minds, they shape how we live. They guide how we treat each other and how we see the night sky. Some of us were told that we were created by a divine breath, shaped from dust, kissed with purpose. Others grew up with tales of cosmic eggs, of gods born from chaos, of turtles carrying the world on their backs. Still others were taught the language of stars and particles, that we are the product of physics, of probability, of cosmic chance. But beneath the details, they all echo the same desire to belong, to understand, to find our place in something larger than ourselves. Even if we never find a final answer, even if the universe keeps her deepest secrets forever hidden, the very act of wondering changes us. It softens us. It stretches us. It reminds us that we are not the center of everything, and yet somehow still a part of it all. When we look up at the stars and ask how it all began, we're also asking, why am I here? What does it mean to exist, to think, to feel, to be made of atoms that once burned in ancient stars? And that perhaps is the quiet miracle, because no matter which model is correct, Big Bang, bounce, brains, or beyond, the fact remains we are here, aware, awake, able to ask. We are the universe, looking back at itself. We are stardust that somehow learned to speak, to wonder, to love. The beauty of this quest isn't in the answer, it's in the asking. It's in the way a child looks up at the sky and asks, what's out there? It's in the late night thoughts that drift between physics and philosophy. It's in the quiet, sacred awe of knowing that something exists instead of nothing. Because maybe that's the point, not to solve the mystery, but to be moved by it, to let it humble us, to let it open us, to feel the gentle weight of being part of something we may never fully grasp. And in that feeling, in that wonder, we find connection to each other, to the cosmos, to the fragile, fleeting miracle of now. So whether the universe had a beginning or not, whether time started with a bang, a bounce, or a breathless silence, we are here and we get to ask. And maybe that's enough. And now, as we return from the edge of the unknowable, one question still lingers softly in the quiet. What if the Big Bang wasn't the beginning? What if it was only a ripple, a spark from a deeper, more ancient flame? Maybe there was no fiery explosion that shouted everything into existence. Maybe it started with a whisper, a slow unfolding, a stillness breaking into motion. Not chaos, but rhythm. Not a bang, but a breath. A beginning that wasn't loud, but gentle, like the tide turning, or a heartbeat echoing through a sleeping cosmos. Because sometimes the most powerful forces don't arrive with a roar, they arrive with silence, with softness, with a single question that changes everything. And maybe, just maybe, the story is still being written by quarks and quasars, by galaxies dancing through dark matter, by time itself curling forward into tomorrow, and by you, yes, you, listening quietly in your room, eyes growing heavier with each word. You are part of this mystery, this ancient question wearing a modern face, this search that began long before telescopes and will likely continue long after we're gone. You are not just watching the story unfold, you are woven into it. Every moment you wonder, every time your thoughts drift toward the stars, every breath you take in the vastness of the unknown, you are part of the universe, asking itself what it means to be. So tonight, if this story stirred something in you, if it gave you goosebumps or peace, or even more questions than you had before, I'd love to know what you're thinking. What do you believe came before the Big Bang? Do you imagine a bounce, a cycle, a multiverse, or something so strange we haven't yet dared to name it? Leave a comment below. Share your thoughts, your dreams, your wonder. Let's build a constellation of curiosity together, one mind at a time. And if you'd like more soft, thoughtful stories like this about the mysteries of space, time, life, and everything in between, then I gently invite you to subscribe to this little corner of calm. Here at the Snoozy Scientist, we don't always find answers, but we always ask. We drift through nebulae and neurons, black holes, and bedtime questions, not to conquer the unknown, but to befriend it. Because the universe is not a problem to solve, it's a wonder to sit with, a lullaby sung in stars, a riddle written across the darkness in glimmers of light. And somewhere in the vastness, your voice matters. So if you're ready for more journeys into the curious, the cosmic, and the just plain beautiful, if you'd like to fall asleep not with noise, but with meaning, then you're already in the right place. Thank you for being here, for wondering, for listening, for being the kind of person who looks up and whispers, "What if?" Now rest easy. The stars are still there. The questions are still waiting, and we'll meet again soon, right here under the quiet sky, for the next voyage into the unknown. Until then, stay curious, stay kind, and sleep well.